All right, guys, welcome. We are going to be doing our Collaboration Core course, this course is going to consist of going through several different lessons, describing the Cisco Collaboration Solutions Architecture, which is lesson number 1, or module number 1, I should say. That's what we're going to be doing this morning. Exploring call signaling over IP networks. We'll take a look at that as well. That'll involve, discussions of IP phones and how they initialize. How does the call process take place for on-cluster calling, call setup, call teardown, signaling, and so on. And we'll get into that. Then we'll take a look at integrating Cisco Unified Communications Manager into LDAP. Also implementing Cisco Unified Communications Manager provisioning features using things like manual provisioning, self-provisioning, as well as batch provisioning tools like the bulk administration tool. We'll also take a look at Codecs in detail. Those are our coder-decoder components that provide us the ability to take our pulse amplitude modulated signals and convert them into PCM signals, pulse code modulated signals, which is essentially our analog wave forms getting converted to a binary format. And we use different audio and video codecs to do that. We'll also talk about dial plans and endpoint addressing. How do we implement MGCP gateways? How do we implement voice gateways? Configuring calling privileges within Cisco Unified Communications Manager. Very, very important concept, calling search spaces and partitions. Implementing toll fraud prevention. Globalized call routing. We'll also take a look at troubleshooting, actually implementing and troubleshooting media resources within Unified Communications Manager. Media resources play a very significant role within Call Manager, and there are 6 different media resources that include things like music on hold, media termination points, conferencing, and so on, transcoding services, and so on. So we'll talk about the different media resources, gateways, and so on. We'll take a look at describing the Cisco Instant Messaging and Presence Platform as well, what we call IM&P. What is Cisco Jabber? We'll take a look at Cisco Unity Connection integration, how to configure Unity Connection call handlers, describing the Collaboration Edge architecture. In that particular case, we'll be talking about things like Expressway C and Expressway E, business-to-business collaboration integration. We'll take a look at analyzing quality issues in converged networks and how do we manage those quality issues. What is QoS and what are the different QoS models? How do we implement classification and marking? And then finally, configuring classification and marking on our Cisco switches. So that's our overall goal for the course. Some of those sections are self-study sections. Some of the sections are obviously sections that we're going to be going through in class. But also, for the video series, we'll be kind of going through all of the different lessons. All right, so we're going to start with talking about collaboration solutions architectures. Now, in this particular section, it's kind of a high-level overview, if you will. We're going to take a look at the Cisco Collaboration Solutions architecture. What are the different deployment models within Cisco Collaboration? Licensing, that's always a challenge with Cisco, is how do we handle the licensing aspect of these applications? What are our high availability options? We talk about high availability from the perspective of running Call Manager servers or Unified Communications Manager servers in clusters. So we'll talk about the different clustering models that are available. How do we provide for capacity planning? What are the security requirements for the architecture? We're going to have a couple of discoveries as well. Discovery 1 using certificates. We'll talk about disaster recovery. We'll talk about the dial plan in detail, IP network protocols. And then we're going to have a discovery number 2, configuring IP network protocols, and codecs. We're going to get into different types of codecs. And then finally, we'll wrap up the lesson by getting into our summary challenge. All right? So as you can see, quite a bit to cover here in this particular section. So the first thing we're going to talk about is what is the overall collaboration architecture, right? What's included in the Cisco collaboration, Cisco Unified Collaboration package or portfolio that Cisco provides, right? There are many, many different applications. The core application that we have within the Unified Communications architecture is our call control platform. Call control can be done through two different platforms, Cisco Unified Communications Manager or IMNP, our Instant Messaging and Presence. Now, our primary Unified Communications Manager call control platform is the Unified Communications Manager platform, what we typically refer to in the past as simply Call Manager. That is my call processing application. IMNP is not a service that has to be implemented. It is a service that is typically implemented. It is bundled with Unified Communications Manager, even though it is deployed as a separate VM, as a separate platform. It provides reachability information and communication information for the individual users that are attached to the Unified Communications architecture. For call control, we use Unified Communications Manager. Call control means how are the devices going to register to the platform? How do we process the calls as far as call setup and call teardown? How do we manage the resources within the architecture? So we'll see within the Call Manager platform that we'll have the ability to provision things like gateways, music on hold, other media resources like conferencing resources, and so on, as well as just our dial plan and dial plan components as well. The Instant Messaging and Presence platform, that's going to be your IMNP service. These can run on, this is a separate platform that would typically run on a separate VM, but it could also run on an ISR router. It could run on a co-resident deployed server, what we call a business edition server. We'll talk more about the different types of platforms a little bit later on, and what kind of deployment options are available for them as well. All right, so we do have options as far as deploying these applications. There are some conferencing components as well. Cisco had a pretty robust telepresence and conferencing package or set of platforms that were available in the past. They've pretty much tried to migrate everything to WebEx at this point. We do see a reference there to Cisco Meeting Server as well as Telepresence Management Suite, what we call TMS. These platforms are being kind of shifted over to WebEx as the primary telepresence platform. But there are still some additional telepresence components that are available. We have lots of different endpoints for video conferencing, some non-immersive endpoints and some immersive endpoints, but we'll get into some of those details a little bit later on. From the Collaboration Edge perspective, we see that in the red box here. Collaboration Edge allows connectivity from anywhere at any time. And there are two major components to the Collaboration Edge solution. One is Cisco Expressway C and one is Cisco Expressway E. Expressway C is what you would run in the core of your network to communicate with your unified communications platforms, and Expressway E is what you would run at the edge of the network to provide things like secure connectivity without having to have the use of some sort of secondary VPN client and so on. So users that are moving around the globe that want to communicate as part of the overall communications platform, they want to be able to utilize their Jabber client, or they want to use some sort of soft phone client, they'll be able to do that securely with these edge platforms. As far as the voice messaging platform goes, there's really only one option for voice messaging, and that's Cisco Unity Connection, or what we call CUC. That's run as a separate platform as well, a separate unified communications platform as a VM. We'll talk, of course, a lot about Unity connection, what types of services it provides. It does not just do voicemail, right? It does many other things. Call handling is one of the major components of this platform as well. And we do that through system call handlers and custom call handlers that we create on the platform to be able to provide some sort of advanced or enhanced call treatment for particular calls. All right. We also have some collaboration management service applications as well. We can see Cisco Prime Collaboration Deployment and Cisco Prime Collaboration Provisioning. The Prime Collaboration Deployment allows us to manage all of our UC applications. We can do things like upgrade software. We can look at our virtual machines. We can do upgrades on existing clusters or do fresh installs and so on. We also have Cisco Smart Software Manager. This is an actual internet-based web portal that allows us to manage the smart licensing on our platforms. You get basically a single management point for the Unified Communications Manager and Unity Connection licenses, which are very, it's obviously an important aspect of managing any unified communication system, having the ability to manage these licenses. We'll talk about that. We actually have a licensing section that we'll talk about a little bit later on. Cisco Prime Collaboration Provisioning allows us to provision our collaboration system configurations. It's basically a template-based configuration system. So we can do moves, adds, and changes through this tool. We can also manage these platforms directly, right? If I want to add a phone, for example, or modify a phone configuration or user configuration, I don't necessarily have to do that through Prime. Prime is an option, but Prime is included if you do purchase the collaboration suite, right? And you want to install Prime to manage that suite. There is a security component to this as well. There are different aspects of security that we concern ourselves with when it comes to a unified communications platform. Obviously, we want to make sure that we're securing the communications itself, right? The RTP audio that's being generated, the media streams that are being generated, as well as the endpoint registrations and endpoint control. But we also want to make sure that we're securing the platform from the perspective of unauthorized access protection, things like toll fraud prevention, having a dial plan in place that's going to ensure that only authorized users are making calls and unauthorized users are being restricted from making calls to certain locations or at certain times of the day and so on. So there are many different aspects of security when it comes to these unified communications platforms and implementing this overall UC architecture. Very important concept. There's also a bandwidth management component that we need to worry about. That has to do primarily with the network infrastructure, right? Bandwidth management is what allows us to incorporate the end-to-end quality of service that's necessary to ensure voice quality. Also, to ensure that we're not oversubscribing links, we're not oversubscribing resources, we're going to implement something called call admission control. Call admission control is a way for us to ensure that the end-to-end quality of the calls are maintained by not oversubscribing links with too many calls that's going to take up too much bandwidth. All right. We'll also talk about, that's part of the self-study section, but it'll be part of the video series as well. Implementing quality of service and doing things like video rate adaptation and so on. And then sizing, right? In fact, let's talk a little bit about the sizing aspect because that's a really important concept, right? Cisco has, when it comes to the unified, or what we call Cisco collaboration architectures, they have several different deployment options that are available. And Cisco has actually created and developed several different documents, and you can get these from Cisco.com if you search on the various things that I'm going to be discussing here over this next section. These documents describe basically what is the design guidance for doing these implementations, what are the best practices for deploying the collaboration solutions. And what Cisco has done is they've developed and tested what they call preferred architectures for different scenarios of deploying unified communications, right? Is it going to be an on-premise deployment where all the collaboration services are deployed and managed on the customer's site or at the customer's location? Is it going to be some sort of hybrid deployment where some collaboration services are going to be deployed on site and others are going to be hosted in the cloud? Or is it going to be 100% a cloud deployment where you have all of the collaboration services that are deployed and managed in the cloud? The Cisco preferred architectures, what they call PAs, provide basically tested and recommended deployment models for these use case scenarios. All right, so it takes a kind of a subset of all of the products from the overall Cisco collaboration portfolio, and typical things that you would run within your enterprise based on specific use cases, and what is the best suited implementation, what's the best suited design for those particular applications. All right. Now, the deployment models themselves, they're going to be what they call prescriptive models. They're built to scale as the need of the organization changes. Now, these platforms, you're going to find out from a scalability perspective, do scale to quite a large environment. We're talking about tens of thousands of phones, right? At a minimum, 7,000, 8,000 phones, depending on the licensing, of course, but tens of thousands of phones. And the PAs, these preferred architectures, are really designed for what Cisco would deem as a large deployment. A large deployment would be any deployment that has maybe 1,000 users or more. The mid to small, or small to medium, I should say, deployments of anywhere from 100 to 1,000 users. But those specific designs are not really defined in the preferred architectures. All right. Now there is different documentation, and I'm going to highly suggest that you guys go out and take a look at this documentation, especially if you're responsible for these implementations within your enterprise. But there are design guides, and the main goal of any design guide, of course, is to define the components and the roles within the preferred architectures. Basically just documents to help you as a customer find what applications are best for your environment, and how do they fit within your environment. That's number one. There's also these things called Cisco Validated Design Guides. These describe the detail of implementation. And the Validated Design Guides provide recommendations for deployments, the best practices for deployments, the procedures and the steps at a high level for the deployments that are necessary as well. All right. And then you also have some alternative design guides as well. These are optional designs that could be deployed as alternatives to the PAs themselves, or to the CVDs. It could start with the main PA as kind of the foundation to build on, and then each alternative design guide can be used in conjunction with those PAs or with the CVDs, as your deployment option. All right. So there's plenty of documentation. And let's see here. Collaboration. CVD. So this is the preferred architecture documentation that I was talking about, and the CVDs. So it talks about, right here, the Cisco Validated Design Guide provides detailed design recommendations and implementation procedures for deploying on-premise preferred architecture for enterprise collaboration solutions. Like I said, they have on-premise, they have hybrid, and they have cloud-based. But basically, it goes through and it talks about how do I handle all these different aspects of deploying UC architectures, right? And you can see actually here, call control is highlighted right here. This is the actual diagram that we have in our student guide here. But then they kind of talk about the different components here. What is the role of call manager? What is the role of IMNP? What does SRST, or survivable remote site telephony, do? So these are great documents to kind of walk through the process of implementing a UC architecture. Who's responsible for conferencing? What are the different conferencing components? You know, is it software-based conferencing? Is it hardware-based conferencing? And so on. So we're not going to go through this in detail, but we will spend some time going through a lot of these applications throughout the course here. All right. Another thing that you want to go take a look at is this is the SRND. This is the reference design guide, the solution design guide. And this also goes into best practice standards for implementing collaboration applications, the current design guide for 12.x. And again, it gets into the details. What are the different components? What are the roles of these components? What is a media resource? What is call processing? For example, if I go to media resources, I get tons of information on the different media resources. So voice termination, transcoding, MTP, trusted relay, annunciator, music on hold, RSVP agent. These are all the media resources that are available within the unified communications architecture. So very important information. So just to summarize here, we've got the preferred architecture. If I could spell architecture documents, what we call the PAs. We've got the Cisco validated design guides, CVDs. We got the solution reference network design guides. SRNDs. And then finally we have the alternate design guides. Probably not something that you guys will see too much, but these are the core documents that most people will reference when they're actually designing and implementing a collaboration solution. They actually have these documents for other, data center solutions as well as security solutions and so on. But we're talking about collaboration, obviously, in this particular case. All right. So this is a summary of everything that we basically just talked about here. So which two components are part of the call control module? Cisco Unified Communications Manager. Unity Connection is the voicemail platform. Meeting Server is part of the collaboration meeting environment. Unified Communications Manager, IMNP, that's part of the call control platform. Mainly with the presence-based applications like Jabber, Cisco Jabber. Telepresence Management Suite is part of the meeting, and then Collaboration Edge is Expressway C. That's the platform that you would deploy inside your network to communicate to Expressway E to be able to allow external clients to communicate. All right. As I mentioned previously, we do have different options for deploying Unified Communications Manager in our environment. Traditionally, these applications would have been deployed on-premise. You would have had the Business Edition server that had all these platforms or architectures implemented there, or you would have had separate, UCS platforms with these different applications installed locally. And that's been for the past 10 years, 20 years or whatever, how Cisco collaboration applications have been deployed. Nowadays, though, we're starting to see kind of more of a mix or hybrid environment where some applications are installed on premise and some applications are being delivered as a cloud-based as a service application. So in the case of collaboration, it typically would be software as a service because we're running a software application in this particular case. It's very rare, but in some cases we might have a cloud-only based implementation as opposed to a hybrid solution. But for the most part, I think most of the deployment models today use a hybrid-based solution. Okay, but regardless, it doesn't really matter where the platforms are specifically deployed. The function of the platforms pretty much remain the same. The only consideration would be, what is the concern for, or what is the consideration for security, for availability, for call quality and call control. Those would be some of the different considerations to take into account. We understand the benefit, obviously, of running cloud-based services, continuous delivery, elasticity, the ability to scale, and be very, very dynamic in our deployments. And hybrid options or hybrid deployment options do give us that functionality. But whether it's on-premise or cloud-based, the applications are going to be the same. You're still going to have some sort of call control application. That call control application is going to communicate with the other call manager or unified communications platforms within your call manager environment to provide additional services. Here in the diagram, we're just seeing kind of some of the common things that are going to be implemented on the on-premise model. The little pentagraph there, the 5 servers that are fully meshed within that box in the middle, represent your core call manager cluster, right? Your unified communications manager cluster. We'll talk about clustering options and how unified communications manager servers cluster for redundancy and scalability a little bit later on. You got your voice gateways for your public switch telephone network or your SIP trunks. You've got your cube. This little box here with the arrows represents a cube. That's what we call a unified border element for communicating with like a session border controller at the phone company. You've got your IM and presence. You've got your meeting applications, your endpoints, of course, your Unity connection. So this little icon right here represents Unity connection. This is my IM&P server. This is my telepresence. These are my telepresence servers. And then my expressway boxes, voice gateways, border elements, and then my endpoints. Of course, you can see that we have the option of implementing all of those things within the cloud, at a branch location. Some of the cloud-based, cloud-only applications would be things like Cisco WebEx and so on. We'll get into the detail of each of these platforms a little bit later on. All right, but collaboration applications, like I said, they can be deployed solely as an on-premise solution. They can be deployed solely as a cloud-based solution, or they can be deployed in a hybrid type of model. All right, in an on-premise deployment, the applications themselves are deployed within the enterprise to provide all the services that we would expect a collaboration application solution to provide, right? video conferencing, content sharing, voice, obviously basic communication, those types of things. So Unified Communications Manager is the key to that whole component, or to the whole deployment, right? Unified Communications Manager is the central platform that provides this integration with all these other platforms, as well as your basic administration. We have IM and Presence, we have Unity Connection, the Cisco Meeting Server, Telepresence Management Suite, and so on. In a cloud deployment, the services are delivered in the cloud. They're going to provide the same basic functionality, right? Voice and video calling, voice and video messaging, meeting, video conferencing, content sharing, those types of things. But it also would include things like WebEx Teams, WebEx Messenger, WebEx Meetings, and so on, what we're using to actually participate in this class today, as well as other cloud-based application solutions, which we'll see a little bit later on as we go through the different discussions here. We also have the Cisco Hosted Collaboration Solution Architecture, what we call Cisco HCS. Now, Cisco, the Cisco Hosted Collaboration Solution is really what Cisco's providing, for the collaboration platform from a hosted model, right? It gives you the advantages of all of the Cisco collaboration solutions, but obviously everything is going to be done from a hosted deployment option. All right, now when it comes to the components, right, the different components within the HCS solution, it really depends on what you're trying to run. There are several different documents that describe running virtual machines or virtual appliances in the hosted solution, and what's supported. So I would definitely recommend that you go and take a look at the Cisco documentation for that. There is one document that specifically I would highly recommend, which is the compatibility matrix document. It talks about the different hosted options that you have for 12.5, 11.5, and so on, and what's supported in the hosted model. So regardless of whether or not you decide to deploy these platforms as a cloud platform or as a hybrid solution or on-premise solution, obviously the configuration, the implementation, and the management of these platforms is pretty much going to be the same. Unified Communications Manager works the same way in the enterprise as an on-premise solution as it does as a hosted solution. So we're not going to focus on deployment architectures too much. We're going to focus on the implementation of these platforms individually, which won't change too much as you move to these different deployment options. All right. If we're doing a hybrid solution, we have a couple of options for hybrid solutions. We can see that here listed at the end of the chapter here. We have enterprise calling with cloud messaging and conferencing. So in this deployment, Unified Communications Manager, Unity Connection, all the basic call control functions, call management functions, and so on, they're going to be deployed on premise. And then things like Cisco WebEx Messenger, WebEx Meetings, IM in Presence, voice and video, they're going to be deployed within the cloud. If I do enterprise calling with cloud calling and messaging, obviously in this particular case, Unified Communications Manager will be deployed on premise, and voice and video calling, WebEx, Messenger, WebEx Meetings, voice and video calling integration, that'll be done in the cloud as well. So depending on, obviously the deployment model that you choose, will depend on the types of platforms that you're going to implement, where they're going to be implemented, and how they're going to be integrated. But again, the main point to take away from this is that these applications are going to be managed, they're going to be configured, and they're going to be integrated the same way, with some minor details on how they communicate with each other, of course. All right. What are two examples of cloud-based services? Well, in this particular case, obviously, WebEx Teams would be a cloud-based service. Cisco Unity Connection could be deployed as a cloud-based service, but it is also an on-premise. There's an on-premise option for that. Cisco Meeting Server, same thing. Unified Communications Manager, the same thing. And Telepresence Management Suite, same thing as well. So Cisco WebEx would be the other choice in this particular case. All right. All right. So the next thing we're going to talk about is licensing. It says here the content is self-study. It's not going to be delivered in the class, but I'm going to go ahead and deliver it anyway because it won't take too long to go through this section here. But collaboration systems 12. Well, pretty much anything 12.0 and above is incorporated with what we call Cisco Smart Licensing or Smart Software Licensing and the Smart Software Manager. All right, Smart Licensing is a cloud-based licensing solution. And I do think it's important to kind of go through how this works in the context of Cisco, because this is something, if you haven't dealt with licensing in the past with Cisco, can be a little bit difficult to navigate. So the Smart Licensing solution by Cisco is a cloud-based software licensing management solution that allows you to automate the licensing tasks that are required within your organization. All right, so you can track the status of your licenses, you can look at your software usage trends, those kinds of things. So Smart Licensing has three major components, right? You can purchase licenses that you need to install within your environment. So self-register, the devices themselves can self-register. They don't need product activation keys, or what we used to call PACs, to be able to activate the licensing. We can track these activations against our entitlements within our organization. You don't need to install the license files on every single node. You basically create what's called a license pool, which is a group of licenses within your organization. And then Cisco obviously has this Cisco Smart Software Manager, which is basically just a centralized portal that enables you as the owner of these licenses to manage all of the licenses from this centralized website. And then there's also a reporting option as well through the portal. So you can view all the licenses that you've purchased, what's been deployed in the network, and then you can use that data to make decisions on your consumption and so on. All right. So in the past, we used to have what we call traditional node-locked licenses. You had to procure the license and then manually install it on the device, and the license was locked to the node. It was associated to that specific device. And there wasn't really an easy way to transfer those licenses from one device to the other. Now, also, those licenses were kind of independent. They had to be managed independently. With Smart Dynamic Licensing, which is what we're talking about in this particular case, there's a call home feature. The device actually initiates a call home feature. It requests the license that it needs. You get pooled licenses. They're no longer node-locked licenses. The licenses are based on the company or they're account specific, and you can use them on any compatible device within the organization. So if you replace a firewall or you replace a router or whatever, you don't have to go back to Cisco and say, you know what, I want to reprovision this device with a new license. You simply just reallocate it through the SmartCare portal or the Smart Licensing portal. So you can activate licenses, you can deactivate different licenses, and these licenses are actually stored on Cisco servers, and they're accessible 24/7 by 365. So you can move licenses between products without having to go through a formal licensing transfer request, which really definitely, assists in managing these devices. If you're doing an RMA on a device, for example, you don't want to necessarily have to go through the hassle of getting a new device licensed. All right. The Cisco Smart Account is the key to this. The Cisco Smart Account is the account where you view all the products. That's where the smart licenses get deposited. And then the Smart Account allows you to manage and activate the licenses on your devices, monitor license usage, track license purchases, and so on. All right. So one of the things that you need to do is you need to go through and set up smart licensing. So the first step would be to place your order for smart licensing. You go to Cisco.com. You obviously go through their terms and conditions governing the smart licensing, and you set up the smart licensing account. So I'm not going to go through the details of the workflow. Basically it's, place an order through Cisco Commerce Workspace or through your Cisco partner. They're going to go ahead and place that order. You're going to activate and use the software. You're going to configure the device to do Smart Call Home, to communicate with the Cisco Smart licensing portal. And then you're going to use the Cisco Smart Software Manager to actually manage the licenses within your organization. All right. Now the Smart Call Home feature is automatically configured once you've enabled smart licensing on the device itself. The Smart Call Home feature is actually used by Smart Licensing to communicate with the Cisco licensing server, which allows the products to basically, on a periodic basis, call home, do an audit and reconciliation of the software usage on the platform, and then based on that audit and usage, be able to identify whether you're in compliance or non-compliance, if additional licenses need to be purchased and so on, and whatnot. All right. There is a Smart Licensing Satellite feature as well. The Smart Licensing Satellite provides an on-premise collector, so we can consolidate and manage all of our smart license usage that way, and so on. All right. So there are some options as well. We can do direct cloud access. This is probably something that you guys are interested in, given the fact the nature of the environments that you're deploying licensing in. Direct cloud access might not be the best option for you guys, right? We can do direct cloud access through an HTTP proxy. We can do mediated access through an on-premise collector, which is connected. The mediated access through the on-premise collector, the products themselves send all their uses information to the locally connected collector that acts as kind of your local license authority. And then periodically that information gets exchanged with databases publicly for synchronization. Or you can do mediated access through on-premise collectors that are disconnected. All right, we still have the same on-premise collector, but in the disconnected model, we send that information to the local disconnected collector, which acts as a local license authority, and then we might do some exchange of information, but not on a regular basis, maybe once a month or something like that. All right. Once a device is registered, the device will receive something called an identity certificate. That certificate is going to be saved on the device, and that's what's going to be used to communicate with Cisco. Every 30 days, Smart Licensing actually automatically renews the registration information with Cisco, and if for some reason that registration fails, you'll be able to see that within the portal. All right, license usage data gets collected as well, and you get a report every month. You can also configure the Smart Call Home settings. so that things like a host name, usernames, and passwords, those kinds of things get filtered out as part of the process. All right, so depending on the type of device, if it's a command line device, you would go into the device and simply say, in global configuration mode, license smart enable, and then you can go through the process of configuring that particular device. We see this a lot, obviously, with routers and so on. With unified communications platforms, manager platforms, very similar concept, but there's a smart licensing portal. When you actually go to the IP address of the device, you'll see that. We'll see that when we get into our discoveries a little bit later on. So that's kind of a breakdown of the smart licensing concept. Now in Unified Communications Manager, it also uses Cisco Smart Software Licensing. Unified Communications Manager, IM&P, they're going to be licensed through Call Manager. And Unity Connection, Emergency Responder, different applications that we use within the environment. So you can see from the diagram here, we have the smart licensing or smart software licensing, and we have things like what we call a Cisco User Connect license or UCL license, or Unified Workspace license. We call that the COOL license. So the basic UCL license provides, this is done basically on a per user basis, which provides access to individual Unified Communications Manager applications. We can see that we have different versions of the software. We have an essential version, a basic version, enhanced plus version. It's a little bit beyond the scope of this class to get into the differences between those, and that often changes. So I would suggest that you go out to Cisco.com and search on CUCM or Unified Communications Manager UCL licensing, and they usually have some matrices and some breakdowns as to what an essential license includes, what types of devices are included in that. Does it include voicemail features? Does it include multiple device registrations? Does it include things like Jabber? That kind of thing. Those are the kinds of things that you're concerned with when you're talking about these different licenses. The Unified Workspace license is really kind of the most popular one because it is a kind of an all-encompassing package. Now there is a standard edition, there's a meeting edition, and obviously the meeting edition is going to include all of the telepresence and meeting information as well. All right. Now, another thing that they discuss here is what they call the Cisco Collaboration Flex Plan. Basically, this gives you the ability to purchase subscriptions. And the idea here is that you have a user-based subscription for cloud-based solutions as well as on-premise solutions. And it gives you the ability to subscribe based on what you need within your organization. Do you need meeting information or meeting subscriptions? Do you need calling subscriptions? Do you need contact center subscriptions, and so on? There's basically a breakdown into 3 different categories. A named user, so you can add cloud or on-premise services to your existing deployments. Obviously the idea is that you're trying to kind of get economies of scale and reduce cost. You can have active users, enterprise management components, and so on. The licensing piece, like I said, my recommendation would be to take a look at what the latest information is on Cisco.com, because the licensing stuff changes on a regular basis. Quite often, actually. All right. So let's see here. Which license type includes a meetings edition and a standard edition? All right. Which license option includes a meetings edition and a standard edition? That would be the UWL, the Unified Workspace Licensing option. All right. That's going to include, that's what we call our COOL license. It's going to include both of those. All right. Now, when we deploy our Unified Communications Manager platforms, we deploy these platforms with redundancy and resiliency in mind. All right, and there are some limitations depending on the type of platform that we're implementing. So what we're going to be talking about in this particular case is our call control cluster, right? Our Unified Communications Manager cluster. Now, before I get into this discussion here, I want to talk a little bit about the overall architecture because it's really important to understand. We have several different applications, obviously, that we can integrate within our Unified Communications Manager system, right? The two key components to these systems is our call control platform, which is Unified Communications Manager. That's what we're seeing in reference to this diagram here. And our voicemail platform, our voice messaging platform, I should say. And that's our Unity Connection platform. All right. Now, we have other applications, right? IM in Presence. We have UCCX, our contact center platform. We have our telepresence platforms, WebEx platforms, and so on. When we're talking about high availability in this particular case, we're talking about our Unified Communications Manager and IMNP systems, all right? Now, one of the key components to any Unified Communications Manager system is TFTP. You see here they kind of mentioned TFTP a couple of times. TFTP, or the Trivial File Transfer Protocol, is the way that our devices register and configure themselves to the system. So it's it is a very important application in our environment, because without TFTP, our devices would not have the ability to provision themselves. The TFTP service can run on any node within the cluster, and depending on how many nodes we have registering to the cluster will depend on if this is going to be a standalone TFTP application or if it's going to be a co-resident TFTP service on a standard Unified Communications Manager platform. All right, but TFTP plays a significant role in how we provision and configure the endpoints within our environment. All right. Now, from a scalability perspective, you can see that we have several different options with regard to clustering. We have a 10,000 phone option, a 20,000 phone option, a 40,000 phone option, and obviously we can have things that kind of fall in between there. But what they're talking about in this particular case is a one-to-one high availability design, right? So if you look at the first box here, we've got basically what we call a one-to-one design, meaning that we have a publisher and a TFTP server. We have a primary call agent and a secondary call agent. Now, keep in mind that when we're deploying these unified communications platforms, they're all running the same software, right? When we're talking about our call agent or a Unified Communications Manager server, right? So when you see the three nodes listed here, they're all running the same software. They're actually all part of the same cluster. And when you cluster Unified Communications platforms together, you have within that cluster, you have something called a publisher, and you have other servers within that cluster called subscribers. The clusters themselves can only have one publisher, right? Regardless of whether or not it's 3 servers in a cluster, 2 servers in a cluster, 9 servers in a cluster, you're only going to have the ability to have one publisher. All right. So when you talk about these servers, right, we have our subscribers, we have our publisher, but they're all running the same software. All right. That's very, very important to understand here. So when you see 3 nodes in a cluster, these 3 nodes are running the same software, right? You have a publisher, and that publisher is acting as kind of the main node within the cluster. That's where you manage the cluster from. That's where the database gets, has full read and write access, where you can update the database and update the configuration. And then that information gets replicated to the other servers within the cluster. Just because the server or the node is acting as a publisher doesn't mean that the node has to act as a call agent. In order for a node to act as a call agent, there's actually a service that you have to enable on that particular node. In fact, let me pull up a diagram here. This is a Visio diagram that I created that kind of breaks down what I refer to as all of the Unified Communications Manager dependencies. And I've been creating this diagram since Call Manager version 4.0. But it has, well, it defines really kind of all of the different features within Unified Communications Manager and defines how these features need to be implemented and what those dependencies are. But one of the things I wanted to mention based on this is you've got your Unified Communications Manager server, all right? It has an IP address, it has a host name, and this service, this CCM service, Cisco Call Manager service, needs to be enabled on that node in order for that node to act as a call agent. So you can run a server without this service running, and that server could be a TFTP server, it could just be your publisher or whatever it might be, but it might not be acting as a registered call agent. All right, and that's a very important concept to understand. There's a difference between a Unified Communications Manager server and a call agent. In essence, a call agent is any server that has phones registered to it, that's acting as a call control platform for those devices. So in this particular deployment model, we have a primary call agent and a secondary call agent. All three of these are running the Unified Communications Manager application. And this server here happens to be a publisher, and these two servers happen to be subscribers. And they have these templates called OVA templates when we deploy these, and this is the template itself. It defines essentially the resources that are necessary in order to deploy or to support this number of devices. And when you deploy the template, you have several different options. Let me show you actually what that looks like real quick. So I have actually VMware running on my computer here, and I'm running Cisco Unified Communications Manager. I've got publisher defined here, but if I come out here and I open up a template, let me go to here, and let's go to Google Drive, Class Shares, Collaboration Core. You see Software OVA templates. These are the templates that you get from Cisco. You can download these from cisco.com, the software page at cisco.com. And these templates basically allow you to deploy these different platforms based on the scale, how many nodes you're going to support on that particular platform and so on. So for example, if I open up the Unified Communications Manager template, all right, it says, okay, I want to deploy CUCM 12.5, and here I can specify the type of node that I'm going to deploy. Is it going to be a 10,000 node? Is it going to be a 7,500 user node? Is it going to be a 2,500 user node, and so on? And then obviously in this particular case, the resources are going to be allocated based on this template. These are templates that are defined by Cisco to scale the platform. And obviously you have to have the right amount of physical resources available on the server, on the physical platform you're installing this on, to be able to allocate those resources to that particular node. So for example, I come here, I'm going to import this, and if I go to edit virtual machine settings, I can see how the machine was actually deployed, right? We have 8 gigs of memory, we have 4 processors, 110 gig hard drive, and then the basic network adapter and so on. Obviously this would be configured for your environment, but these are the recommended settings. Even though I could go up to 32 gigs on this computer, 8 gigs is the recommended for this particular platform. So obviously you'd have to have those resources available on the physical platform that you're deploying the server on. All right, so that's what they mean by these OVA templates. Now, when you deploy the cluster, let's say we deploy it as a 10,000 node cluster, the one-to-one design model means that we have for every publisher, or excuse me, for every call agent, primary call agent, we have a secondary backup call agent. The phones actually register to these servers using something called a call manager group, and they can actually register up to 3 different servers. They can register to a primary server, a secondary server, and a tertiary server. They can have up to 3 servers within a call manager group to provide you basically 3 levels of redundancy. In this particular case, the call manager group includes only 2 servers. So all of the phones within the cluster are going to register to this primary call agent, which is not a publisher, it is a subscriber. It is a secondary node within the cluster. The publisher is the primary node within the cluster. Every cluster includes at least 1 primary node. At the most 1 primary node, I should say, a publisher. And then it can have multiple secondary nodes, which we call subscribers. All right. Obviously, we want to make sure that we provision these servers the same. If this primary node is provisioned as a 10,000 device node, then the secondary node would be provisioned as a 10,000 device node as well. All right. Oh, by the way, all these scaling options and all these scaling deployment options are part of the SRND. They're part of those Cisco validated designs and so on. So definitely take a look at that. In a 20,000 node cluster, we still have a separate publisher. We still have a separate TFTP server. Again, the publisher in this particular case is not acting as a call agent. It's simply acting as essentially the server that manages that allows us to manage the database. And then we have 4 subscribers within this cluster. All right, we have a primary subscriber for the first 10,000 phones with a backup server for them. We have a secondary subscriber as the primary call agent for the other 10,000 phones and the backup for that server. We could actually even take this one step further, right? I could say, okay, I want this primary and backup server to be backed up by this backup server. So I could have 3 levels of redundancy in this call manager group. So I might have, let me do this in Notepad here. In this particular design, I might say, okay, call manager group A, right? Call manager group A is going to include P, the blue one, and B, the blue one, and then B, the red one, right? So that would be, you know, kind of how I would establish the redundancy for those first 10,000 phones. And then call manager group B might be the publisher or the primary call agent for red, then the backup call agent that's red, and then finally the backup call agent that is blue. Does that make sense? So you can use multiple servers. You can reference multiple servers, or the same server, I should say, in multiple call manager groups. Just keep in mind that if for some reason this could be a worst case scenario, this primary and backup server here fail, and this primary server fails, you're going to end up oversubscribing this server with 20,000 nodes, which won't work, obviously. But you know, that would mean 3 different independent failures would have to occur for that scenario to kind of manifest itself. All right, but again, you can have up to 3 call agents within a call manager group. Here's our 40,000 node cluster. Same concept. We have an individual publisher to manage the database and to do the database replication. We have TFTP running co-resident on that particular service enabled on that particular platform. And then we have our our primary call agents and our backup call agents for each of the 10,000 phones within the cluster. This is ideally how Cisco would like you to deploy Unified Communications Manager, because obviously in this case we're having to license multiple nodes, right? But with the pooled licensing and whatnot, this actually doesn't become too difficult of a task. All right, each of these, so we would have essentially 9 virtual machines that are deployed here. And each of those 9 virtual machines, they're still within the same physical cluster. All right, so they're still communicating with each other. And there is a ICCS intercluster communication service traffic that's being replicated between those servers within the cluster. All right. There is another option, the 2-to-1 option. Now, from a 10,000 phone perspective, the model doesn't really change because you really only have 2 call agents within this design anyway, right? You have a primary call agent and a backup call agent. But as we start to scale, we start to get to a larger phone count, like a 20,000 phone count or 40,000 phone count. For every 2 primary call agents, we only have 1 backup call agent. All right? So that means that we're banking on the fact that both primary call agents would not fail at the same time. If both primary call agents failed at the same time, we would not have enough resources to be able to allocate those resources to the entire cluster. But the idea here is that we're trying to kind of hedge our bet a little bit and say, you know what, it's highly unlikely that both of these publishers, excuse me, I keep calling them publishers, they're not publishers, they're subscribers, but both of these primary call agents would fail at the same time, and that's highly unlikely. So again, 2-to-1 model here. For every 2 primary call agents, you have 1 backup server. Again, you could still set up a tertiary server as well if you wanted to. Take this one step further if you wanted to, right? You could say, you know what, I'm going to go to a 3-to-1 model. And the 3-to-1 model would be for every 3 primary call agents, you'd have 1 backup server and so on. It really just depends on what your budget is, right? And what your overall goal is. We can still add other features within this as well, right? SRST, Survivable Remote Site Telephony. And we can do that for voicemail as well as call processing. We'll talk about SRST a little bit later on, but we can actually implement a lot of the call processing services and call processing features on a Cisco ISR router, so that if a WAN link goes down or we lose connectivity to our cluster or call agent, the phones can register to the ISR router and they can get their basic call control functionality from the ISR router. And by the way, those ISR routers can scale up to hundreds and hundreds of phones now, not 10,000 phones. You're not going to find a SRST option that's going to support 10,000 phones, but certainly hundreds and hundreds of phones. So for a branch office or a remote office, or even even the headquarters office where you want to have basic connectivity for the users, that would be something that you could implement. All right. We'll get more into the whole idea of how a cluster is built and how we define the servers within our Unified Communications Manager platform and so on later on. All right. Which redundancy scheme provides high availability during upgrades and simplifies configurations? Now, in this particular case, the 1-to-1 model would do that, right? The 1-to-1 model would provide you the most flexibility when you're doing, software upgrades and where you have to reboot servers and so on, because obviously you'll always have some sort of call agent available for the phones that are registering to the server itself, because you have, for every primary server, you have a backup server. All right. Now, keep in mind, when we're talking about these deployment options, each of these boxes represent a separate virtual machine, a separate physical well, not physical server, but separate logical server deployed on in your VM environment. You can do clustering over the WAN. You can do clustering across geographic boundaries, but there are very specific requirements in order for that to take place. There's basically two types of replication that occur here. And we're going to get into this a little bit later on when we get into the actual communication, the network traffic that's being generated with these deployments. We'll get into that in more detail a little bit later on. But inter-cluster communication as well as database replication services that run between the servers. ICCS traffic is real-time status information about endpoints, their status, their registration status, their deployment status, and so on. But database replication is when I make a change to the publisher, that information needs to be pushed down to the subscribers within the cluster so that everybody within the cluster has the same information. All right. All right. Obviously, capacity planning, as the name implies, is how do we size the system, right? How do we make sure that the system is accurately sized? Sizing the system is going to be very critical, obviously, in order for us to be able to support the number of devices that we want to have within our environment. All right. There are some specific factors, and I would again say that you should take a look at the validated designs and the SRND to make sure that you're sizing and scaling the environment correctly. But there are several factors that go into this, right? What are the sizes of the clusters themselves? Am I going to use a centralized cluster deployment? Am I going to use a distributed cluster deployment? The size of the clusters are very important. How many servers am I going to have in the cluster? And that's going to be based primarily on the number of endpoints that I'm trying to register within that particular cluster, and also the redundancy model that I'm using for that particular cluster. Am I using a 1-to-1 redundancy model? Am I using a 2-to-1 redundancy model? And so on. The cluster could have high utilization. If you, for some reason, a single cluster doesn't work. Remember, we can only support up to 40,000 phones in a single cluster, so we may actually have multiple clusters that we have to deploy with trunking between those clusters to be able to communicate between the clusters. If one cluster becomes overly subscribed or overly utilized, do I go into a second cluster, and so on. All right. The interaction between the products is really important as well, right? Because we're talking about right now just simply deploying things like Unified Communications Manager. But what if I'm deploying WebEx meetings, or I'm deploying telepresence, or the edge components like collaboration edge components like Expressway C and Expressway E, and so on. So we obviously have to have communication between that as well. There is no actual hard set predefined limit to these particular servers, right? So a node might support 10,000 phones, but it might not support 10,000 phones if you're running a whole bunch of other services on that node. If you're running TFTP on that node, you're running conferencing on that node, you're running a bunch of MTP resources on that node, you may end up being able to support fewer endpoints on that particular node because the node is being used for other services as well. So the server's capabilities, what you have deployed on that server, is going to be pretty important as well. So depending on what you're deploying on the server. The capabilities of the server is important. We have different types of platforms, physical platforms that we can deploy this on. It could be an ISR router. It could be a business edition type of platform. It could be a very robust data center class UCS server. It really depends on the physical platform. And of course, that server's physical capabilities are going to limit what you're able to do on that particular platform as well. Are we implementing other features, right? Are we doing call detailed reporting and call management records? Do we have different types of calls? Because different types of calls will consume different types of resources. If the calls are happening between phones in the same subscriber, for example, or if the calls are happening between two different subscriber nodes within the cluster, or is it a call between two different clusters, or a call between a node within a single cluster that's going to the PSTN and so on. So there are considerations that we have to take into account based on the call flow and how call control is taking place. What types of endpoints do I have? Do I have phones and gateways? Are these fully immersive endpoints? Are they basic analog endpoints? Whatever they might be. What is the software version I'm running? Am I using external applications, right? Am I using CTI integration, computer telephony integration, to communicate to external applications? All right, so the sizing, I guess the point is the sizing it's not really a hard set number. If I use the OVA template to build a 10,000 node call agent or subscriber, that doesn't guarantee that particular platform is going to support 10,000 nodes, 10,000 endpoints, excuse me. It really depends on the other things that I'm running on that particular platform. All right. We also want to make sure that we're planning for growth. We're planning for peak usage, average usage, and so on. All right. Now, Cisco does provide some tools that are available to us to be able to manage these, this design. Again, my recommendation would be to follow the Cisco validated designs. It's very rare, quite frankly, in most enterprise environments that you're going to have 40,000 endpoints. It's actually kind of rare to even have 10,000 endpoints. We've done a lot of implementations for our clients, and most of those implementations are, at the most 5,000 nodes. I keep saying nodes, 5,000 endpoints, right? But it really depends on your enterprise. All right, there's the Cisco collaboration sizing tool. That collaboration sizing tool, which you guys are going to take a look at a little bit later on in one of your discoveries, allows you to size different products. Unified Communications Manager, IM&P, your voice messaging platform, your gateways, your call, the suite itself, the whole Communications Manager suite based on compatibility between the different endpoints or the different types of endpoints, and so on. So that's a useful tool. The Cisco Unified Communications Manager Management Edition is the SME sizing tool, basically for session management. You got VXI sizing tools, you got virtual machine placement tools. So let's see here. We have a question at the end here. Which sizing tool is a graphical tool that allows you to choose a tested reference configuration, TRC, or specifications-based hardware? Is that going to be the VXI sizing and configuration tool, the Cisco Unified Communications Manager SME sizing tool, the collaboration sizing tool, the virtual machine placement tool? And in this particular case, it is the virtual machine placement tool. That's the trusted resource configuration. I mentioned that briefly as we were kind of going through those different links on the page I was just showing you. But yeah, the virtual machine placement tool is what allows us to do that tested reference configuration. Keep in mind the TRCs are what allows us to define the physical resources that are required on a platform to support the different deployment architectures that we're trying to deploy, the different deployment models that we're trying to deploy. All right. So there are many different security features that are available within the Unified Communications Manager architecture as well. Like I said, these could be security elements that are used to secure the actual voice communication, what we call the media stream security using secure RTP, the real-time protocol. It could be secure endpoint registration using certificate-based endpoint authentication, so that when a device authenticates to the or registers to the cluster, it authenticates to the cluster and then completes the registration. It could be infrastructure security components like access control lists within the architecture that allow specific ports and protocols through the network. It could be our firewalls, authentication services, and so on. And in addition, we also have security components that are involved in securing the platforms themselves, right? Administrative access, what we call role-based access control, where we have specific rules that are applied to being able to access these platforms. And, you know, we can have multi-level admin configurations where you might have one administrator that has the ability to manage and configure phones, and then you have another administrator that might be able to manage and configure the dial plan or gateways or something like that. So we have that capability where we can define specific users, application users within Unified Communications Manager, and we can say, okay, these specific applications users have access to you know, resource X, Y, and Z, and so on. We can even define it as read-only access or read-write access or full access. So securing our Unified Communications Manager environment is actually multifaceted. There are many different considerations that we have to take into account when we're considering how to secure the platforms. And we'll talk about the security a little bit later on. All right. Obviously, when it comes to telephony across the network, that data is only as safe as the devices that are actually transporting that data. So it's an end-to-end security concept that we need to employ here. But there are ways that we can do that without having to run traditional security architectures, right? We can do encryption with TLS and MTLS. We'll talk about that in a little bit here. But, you know, the same basic concepts that we would use to secure our data within the network can be used to secure the transport of our IP telephony traffic as well. All right. So when it comes to securing, say, the media, all right, we have, for example, devices that want to register. We have the ability to use things like mutual transport layer security, or TLS-based security, certificate-based authentication, right? TLS basically is a way for us to encrypt TCP traffic, and TCP traffic is not going to be our media streams, but the TCP traffic could be things like our call signaling and call control applications like SIP and so on. So let's say we have, in this particular diagram, we have a TLS client that connects to the TLS server. It sets up a TLS connection. The client establishes that TCP connection with the server by sending that client hello message, which contains random numbers for security purposes, as well as the client's capabilities, and you know, what are the cipher suites that the client supports, and so on. And then the TLS server selects one of those particular cipher suites, and then authenticates that client. So this is kind of a way of to allow us to establish the communication channel between the endpoints. Now, another function that we have available to us, and this is more specific to what we see with Cisco Unified Communications Manager, is the ability to support certificate trust lists. The CTL functionality is more specific to phone security, and it provides basic functionality within Unified Communications Manager. It includes things like certificates that UCM uses to authenticate endpoints. We authenticate the downloaded files, like the configuration files, the locale files, the ring lists, and we do this by using a signing key. This also, CTL, allows us to encrypt the TFTP configuration process using that signing key, encrypt the call signaling for the phones themselves, whether it's skinny signaling, SCCP, or SIP signaling, And it also provides us the ability to encrypt the call audio, the media as well for the phones. All right. There are basically two functions that are provided by securing the phone communication. We can do the CTL provider encryption using TCP port 2444. That would be the device that's actually providing the CTL token. We can do TFTP, which is UDP port 69, or CAPF, TCP port 3804, SCCPS, that's Skinny Client Control Protocol encryption using port 2443, SRTP, secure RTP. RTP is going to run over different ports, UDP ports, specifically the even numbered ports, 16384 to 32768. But the ITL and CTL certificates, ITL is the initial trust list. That's basically your authentication mechanism within Unified Communications Manager. And CTL is your encryption for the signaling and the media itself. All right. The CTL is a certificate-based solution. It does require certificates. There really isn't kind of any difference between what CTL does and what a typical certificate-based authentication process does. But we'll get into the details of the authentication a little bit later on. We have to talk about, what is tokenless authentication versus token-based authentication, or what we call mixed mode authentication. What are the services that need to be enabled in order for us to run mixed mode authentication and so on. We'll get into that a little bit later on. All right. All right. Which of the following supports two-way authentication? In our particular case, that's obviously going to be TLS. We talked about that as part of our, part of this section here. All right. So the answer in this particular case is MTLS. Sorry, MTLS. Meant to say MTLS. Right? If you recall, MTLS is the mutual transport layer security, where the server authenticates the client and the client authenticates the server. Traditionally, the client would simply authenticate the server, and the client would not have to authenticate itself to the server. We would just authenticate the server itself. But MTLS provides that mutual authentication. All right. All right, so we're going to go ahead and get into discovery number one in this first module. Discovery number one is using certificates. Now, in this particular discovery, we're going to be just kind of taking a look at how we implement mixed mode operation. Mixed mode is required in order for Call Manager to be able to process encrypted communication. And mixed mode means that basically Call Manager is going to be able to process both encrypted and unencrypted signaling for the devices that are attached to the cluster. By default, mixed mode is actually disabled. That means that you're only going to be able to support in unencrypted calls in the Call Manager environment. Starting with UCM version 10, mixed mode is enabled by default. Before version 10, we had to implement it using two different hardware keys. We would actually go into security parameters. We would go under cluster security mode settings. And by default, that setting would be set to 0. And that would be, by the way, under the enterprise parameters page. And we could enable mixed mode. We would basically connect to the command line of the Unified Communications Manager, and we would run the command utils ctl set-cluster mixed-mode. And then once we go back into the enterprise parameters and view the cluster security mode, that value would be set to 1. That's not a value that we would actually be able to set within the cluster or within the GUI and within the enterprise settings. Now, Call Manager does have lots and lots of different types of certificates. And what we're going to take a look at in this lab is going to take a look at the server and the certificate authority certificates. Server certificates are going to be used to validate that a PC or an endpoint that's actually connecting to the network can be trusted, or whether or not there's an inherent security risk with those particular devices that are attaching to the network. So Call Manager is going to send a certificate request to the certificate authority, and then that certificate authority in turn is going to issue that certificate. These certificate authorities are typically issued by, the server certificates are typically going to be issued by a certificate authority, and then when the CA receives that request for that server certificate, we do a check to request, to verify that the actual signing request and certificate generation request is valid, and that can happen through various different checks, but if the check passes, we're going to issue the certificate, which then can be loaded on the server. All right, so when a device connects to the server, the device is going to receive a copy of that identity certificate, and assuming they trust, the chain of trust is created with the issuing certificate authority, we can be sure that the server is legitimate, that the server is safe. It's just like any other type of certificate-based authentication that we have with web servers and other types of servers that require signed certificates from a third party. All right, now there are many different public CAs. There's quite a few, Symantec and VeriSign and Thaught or Thought, Network Solutions, and so on, that can actually issue certificates. The public certificate, the public CA issued certificate is actually required on the servers that are actually providing the service. So Cisco Expressway E, as an example within the unified communications architecture, online banking services or servers, secure payment sites, anything that's basically on the public internet that needs to be trusted is going to have some sort of certificate. Users that are connecting to the public server will need to be able to trust the CA that actually issued that certificate, that server certificate, and accept the connection to that particular server. Now, if the public server held a server certificate for an unrecognized CA, the connection would be rejected, even if it is technically a valid certificate, because the chain of trust is broken in that particular case. So we do need the public certificate of the signing CA. We need to trust that certificate. That needs to be part of our certificate store. And then in turn, because that certificate, that identity certificate that's being provided by the server, the Call Manager server in this particular case, is signed by that CA, we have that kind of transitive trust that we're going to have with the CA. All right, now private CAs could be deployed behind the firewall. They could issue certificates that will then be accepted within the enterprise, but these certificates are not going to be recognized by a third party. Private CAs are local to the enterprise, so it's basically provides you that enterprise level certificate authority function. It's not as secure as a public trusted CA, but it still it's certainly better than just blindly trusting the Call Manager server that we're connecting to. So we can create and use our own certificates in that particular environment, and this is what we would refer to as self-signed certificates. When we use a certificate that's not signed by a public entity or not signed by a public certificate authority, we define those as self-signed certificates. This is going to save the enterprise, obviously, lots of money, well, potentially lots of money, depending on how many certificates you're deploying in the environment, because the internal servers, and in our case, we're talking about Unified Communications Manager, doesn't need to be recognized by the third-party users. And there are many, many different types of private CA software solutions as well. All right. The certificate validation process uses what we call an asymmetric encryption process to ensure the authenticity of the certificate. All right. The way that this basically works, let me go ahead and pull up a diagram here, and I'll kind of jot this down. Let me change this to a bigger size. So let's go ahead and start the process by, this is our call manager server in this particular case, and let's just say that we have a phone that might be attaching or communicating with that particular call manager server. Now the server itself has already gone through the process of sending up the certificate signing request to that CA that exists. I don't know why my monitor is acting weird, but let's try that again. To that CA that's actually doing the signing request, and then the CA in return is going to issue the certificate to the server. So that's our identity certificate that we use, which is our public certificate that is digitally signed by the CA that gets installed on the call manager server. And what happens when the phone communicates to the call manager server, that identity certificate is then going to be sent to the phone that references Unified Communications Manager. And because we also have the public certificate of the CA installed, the identity certificate of the CA, which is the public certificate of the CA, we can then go ahead and verify the digital signature of that particular certificate that's being supplied by call manager. And that's the general concept. Now, the reason this is called an asymmetric encryption process is not only are we authenticating the call manager server, right? So we're trying to go through the process of actually authenticating this call manager server, but we're also trying to establish a secure communication channel. So what's going to happen is the client is going to generate some sort of key material, all right? And we're going to take that certificate that we got from the call manager server, and we're going to encrypt that key so that we can then in turn send that key over to the server, all right? And then the server is going to take that key material. So we have this key material that we've received on this side, which again is encrypted with the identity or public certificate of the server. And we're going to use the corresponding private certificate because we have both the public and private certificates. These are kind of paired together, if you will. We're going to use that private certificate to then decrypt that key so that we have a key that we can use. And then that key, along with the key that was established over here, is what we're going to use to establish our encryption tunnel. All right, that's our shared secret key. So overall, that's kind of the entire process, if you will, of doing this certificate-based authentication. It provides for integrity, it provides for authentication of the call manager server to the endpoints that want to communicate. And then in addition, it provides us the ability to establish the encrypted tunnel, which is a symmetric process, by using this public and private key pair, and then in turn giving us the ability to exchange that key that we're going to be using for the encryption process. All right, and that's really what the goal of this particular discussion is to take a look at that. That certificate validation process is what we refer to as an asymmetric encryption process. We're ensuring the authenticity of the certificate. We use two keys, the private and public key. Anything that gets encrypted with that particular public key can only then be decrypted with the corresponding private key. Now, if I was just using this for identity, I might encrypt something with the private key, and then I could in turn decrypt that with the public key. That doesn't ensure any confidentiality, but it does provide an ability for us to be able to identify the user or identify the source of information. We use that for like digitally signing emails and so on. So that private key is always going to be securely held on the CA server, assuming we're using the identity certificate of the CA to verify the signature of the certificate that's being presented. But the public key is going to be published, and anybody who wants to can download that public key. They can in turn trust that public key, And they can also use that public key to unencrypt the certificate. Once the certificate is unencrypted, then we can verify its identity, and we can verify that that certificate can be trusted. All certificate authorities publish a CA certificate. That published CA certificate includes that CA's company information. It includes a time period that the certificate is valid, as well as a copy of the CA's public key. So the clients themselves, PCs, phones, other servers, they have to contain in their trust store that recognized CA certificate. If it's a brand new CA, it has to be recognized, and then that certificate will have to be acquired and actually uploaded to the certificate trust store so that we can then in turn identify the trust of that particular individual. Okay, so to get the certificate for a specific server, the first thing that has to happen in that process is we have to generate that certificate signing request, right? That's how we're going to get issued that identity certificate for the CUCM server. I don't know why that's doing that, but the CUCM server that will then provide us the ability to identify that server within our topology. Does that make sense? All right. That certificate signing request contains all of the information about the server, the company's information for the company that's actually requesting the certificate. That's then going to get passed to the certificate authority, which generates the public certificate, and so on. Now, when we go through the process of generating the CSR, the system's going to create the private and public key pair for the server. The private key is never going to be distributed, not even to the CA. The public key is going to be included in the signing request, and then that's going to be published in the server certificate that we then can present to the devices that are attaching to Unified Communications Manager. Okay? Now, Cisco Unified CM requires a CA and a server certificate gets uploaded for each service across the cluster. As an example, a CA and server certificate must be uploaded. It's going to have to get uploaded, say, for example, if we're running the Tomcat service, or maybe it's going to be uploaded if we're going to be running the Call Manager service. All right, the certificates can be at the same CA, but the certificate could also be uploaded once for each service, and it doesn't necessarily have to be something that's signed by the same CA, although it'd be unlikely that we would do that. All right, any service that supports certificate verification is going to have a certificate, and there are basically 5 different services that run within Call Manager that are going to require these certificate-based services. There's the Tomcat service. That's for the CM HTTPS server. So if you're accessing any kind of HTTPS service from Call Manager or IM&P, that's IM in presence, you're going to use this certificate to validate the server in that case. There's the Call Manager certificate service, right? Any application, any endpoint, Jabber clients, anybody that's accessing the Call Manager service is going to use the Call Manager certificate to verify the Unified Communications Manager server's identity, before maybe the device registers to Call Manager and so on. There's also what we call a CAPF certificate. This is used to align with the global certificate policy for CAPF with other services. So rather than CAPF being, say, the root CA for the LSC certificate, it will be the intermediate CA, and the main CA will be the root in that particular case. We'll talk more about the CAPF certificate a little bit later on. There's also an IPsec certificate that would provide us the ability to establish IPsec tunnels between the gateways and Unified Communication Manager. And then there's also the TVS, which is the Trust Verification Service. That's used to actually, these are certificates that are used to actually verify the trust verification service connections. So in this lab, what we're going to look at, it's a simulation. We're not actually doing the work in this particular case in this lab, in this discovery. In the other discoveries, we'll get into actual hands-on configuration. But this is kind of a simulation that allows us to take a look at creating the certificate signing request for call manager, creating a certificate from that certificate signing request, and then uploading the certificate to the call manager. All right. It is based on real-life tasks and real-life equipment. We just don't use physical equipment in this particular demonstration. All right. So the first task that we have is to create a certificate signing request for the call manager service. All right. So the first step that we're going to have to do is we're going to have to go over to security, and then we're going to have to go over to certificate management, and then we're going to say generate a CSR. All right. And you can see here from this drop down, we can identify the purpose of that particular certificate. We can pick one of the choices here. Is it an IPsec certificate? Is it Tomcat? Is it call manager? Is it CAPF? Is it TVS? And then we can specify how we're going to distribute that certificate. In this particular case, we're going to select call manager for the certificate purpose, and then we're going to simply select generate. And you can see that the success notification popped up, right? Certificate signing request, created. All right. So we're going to go ahead and close that out. And then the next thing is, assuming we've gone through the process, so we've gone through the process of actually completing that signing request, we're going to go ahead and click download the CSR. That's the certificate signing request. Again, we have a choice of selecting the certificate purpose. Normally we would see the other options there, like Tomcat or call manager. And we're going to select call manager, and we're going to download that certificate. You can see at the bottom of the screen there, we see the file called callmanager.csr. Now, to view that file, we actually could go into the File Explorer. Well, let's just go to the File Explorer icon here, and we can actually go over to the downloads, and we can go to our call manager option. And then this is the certificate that was actually generated in that certificate signing request. Obviously, it's in machine language, so we can't really see, but we can see that it is a certificate request. The file is actually encrypted, but we can actually see the purpose of the file. In this case, it is a certificate request, which means that we have actually generated a certificate signing request. If we're using a public CA, this file should be uploaded to their website when we're actually ordering the certificate. It might be done automatically if we have an automated process that will allow that to happen, or it's something that we might have to do manually. If we're using a private CA, then the contents of this certificate signing request should be pasted into that certificate creation software that will then allow us to generate that certificate. So we'll go ahead and close this out. Let's see, close. Why is it not closing? I think because my screen here, let me try my mouse. There we go. And we're going to go ahead and close out the File Explorer. All right. Now again, we're using a flash demonstration in this particular case, so it's not quite working the same way, but so we're going to go ahead and close out our File Explorer, which we did, and we're going to close out the download, click close on the download CSR, and that will provide us, let's close that. All right. Now, there are different certificate formats that exist as well within Unified Communications Manager. We use either a privacy enhanced mail version or a PEM. That's going to be your standard X.509 certificate that's going to be encoded based on base 64 encoding and encryption. And that's going to be supported by things like Cisco VCS as well as Cisco Call Manager. It really is kind of the most common format that you're going to see within Unified Communications Manager. And then we have something called the DER. That's the Distinguished Encoding Rules. That's going to have our X.509 certificate, but it's going to be encoded in a binary format. That's only supported by Call Manager, but none of the other Call Manager applications. So the PEM X.509 certificate is probably going to be the most common that you're going to see. The primary difference between the two types is simply the way that the certificate is encoded, but with Call Manager we can support either format. Expressway, meeting server, other unified communications platforms are only going to support the PEM format. So if we are using other UC products for consistency, we'll pretty much kind of standardize on the PEM format. All right, our second task is to go ahead and create a certificate from this certificate signing request. So we're going to use the Microsoft Certificate Service to generate the server certificate. We're actually not restricted to using this certificate service. There are many kind of solutions available which allow us to generate a PEM or DER formatted certificate. All right, so let's go ahead and go into the second tab here. And this is our Microsoft Active Directory Certificate Service that we already happen to have open. And we're going to go ahead and say request a certificate. And then we're going to do an advanced certificate request in this particular case. All right. Now we want to go on into the File Explorer. And we're going to go ahead and go to our downloads and our Call Manager certificate. And we're basically going to copy this information. So we're going to go to Edit, select all, and Edit and Copy. We can go ahead and close that out. And we're going to go ahead and close that window out. And we should be able to paste that information into that window. It's just text, so we should be able to paste that information in it. All right, so we're going to go ahead and right-click, and we'll just paste that information in there. Okay. All right, now that information is populated, we can hit the Submit button. All right, and we can see that we can specify the type of certificate. We could do a DER encoded, which is our binary encoding, or we can do our base64 encoded certificate. We're going to select the base64 because that's how the certificate was generated. All right. Now, before uploading the certificate, we need to download the CA certificate. What's going on? Well, let's start by going to Download Certificate here. All right. And then we're going to see download a CA certificate or the certificate chain. All right. Now we want to make sure that we have base64 selected because again we did a CSR for a base64 certificate, and then we're going to click on download the CA certificate. All right. You can see there that we have certnew.cer, and then we have certnew1.cer. The certnew was the original signing request that we did, and certnew1.cer, certnew1.cer is the one we just generated. All right, or at least downloaded anyway. Now the next step is to upload these certificates to Call Manager. All right, so we're going to go back to Call Manager, and we're going to go to Upload Certificate or Certificate Chain. All right, it's pretty straightforward, this process, right? We're going to choose the file that we downloaded. So the first thing we need to upload is the actual CA certificate. So we're going to select the Call Manager Trust in this particular case, and we're going to choose the file that we're going to upload. And we have our CSR file as well as our certificates. We're going to select our certnew1, which is the CA certificate. And then we're going to select Upload to upload that certificate. All right, it says the certificate was uploaded. We do need to restart the Call Manager service or any service that's relying on this particular function to be able for that service to utilize this particular service. All right, we're going to leave this window open for now. We're going to upload our server certificate now. So we're going to go ahead. We're still going to, in this case, select the Call Manager certificate. The Trust certificate was the CA's certificate. In this case, we're going to upload the Call Manager certificate. we're going to choose the file and we're going to choose cert new, click open, and we're going to go ahead and upload that certificate. All right, so we need to make sure again that the server's running in mixed mode. We see an indication of that. If the cluster is in mixed mode, please regenerate a CTL file. That's the certificate trust list. We talked a little bit about that in our discussion earlier, and make sure that the endpoints download that updated CTL file. So we might have to reset the devices in a device pool and so on. So we see that we've successfully uploaded the trust certificate for the CA, as well as the certificate for the server, and we can basically see that in the output here. Success, success, restart the services, and so on. So now we can click close, and then we can actually go into the find option, and we can actually see the certificates that are actually installed, right? We see the, in this particular case, the second one in the list, call manager, cucm-pub.cll-collab.internal. It's an RSA. That's Rivas, Shamir, and Edelman, basically the guys that came up with this asymmetric PKI structure and asymmetric certificate-based authentication process. And then on the fourth one down, we can see our call manager trust certificate, which is the CA's certificate. Notice it says issued by the certificate CA. Both of them are issued. The distribution, one is for the CA and the other one is for the call manager. We can kind of see that in this the description here. All right, so that's basically the process that we go through, right? And these are the two certificates that we actually uploaded. This one right here and this one right here. All right, and this is what I was referencing, talking about who this certificate was issued by, the validity period. This is pretty important as well. You notice that the validity period for this certificate is for 1 year, but the validity period for that certificate is a little bit longer. So it really will depend on how the certificate is issued, and that's what's going to determine how long that certificate is going to be valid for. All right, so that's basically our demonstration, our first discovery. We're going to go ahead and continue on. We're going to a couple more topics, and then we will also get into discovery number 2. All right, so the next thing we're going to talk about is our disaster recovery. Within the Unified Communications Manager platform, there is a component called the Disaster Recovery System, which we simply refer to as DRS. It's actually part of all of these different platforms. IM&P has a DRS component, Cisco Unity Connection has a DRS component, Contact Center Express, and Unified Communications Manager. This disaster recovery system can be invoked from the main login screen. When you go to the main login screen, at the top right corner of the login screen, regardless of which application you go into, regardless of which unified communications application you go into, at the top right corner of the screen is a primary navigation pane that allows you to switch between call manager administration, OS administration, reporting, disaster recovery, services administration, and so on. So you would go to the top right corner of the screen and you can invoke this disaster recovery system, which provides full data backup and restore capabilities for all of the servers that exist within your Unified Communications Manager cluster. So you can do regularly scheduled, automatic, or user-invoked data backups from here as well. The disaster recovery system itself performs a cluster level backup, which means that it's going to collect the backup information for all the servers in Call Manager and inside that Call Manager cluster to a central location, and it's going to archive that backup data to a physical storage device. All right. DRS also restores its own settings, meaning that if you have backup device settings or schedule settings that are set up as part of your DRS system, the DRS system is actually going to back up and restore that part of the configuration as part of the platform backup and restore function. The disaster recovery system backs up and restores what we call the drf device.xml and drf schedule.xml files. Those are the files that are specific to the backup device settings and the schedule settings. When the server is actually restored with those particular files, you're not actually required to go back and reconfigure your backup devices and the schedule. All right. Now, when you perform a system data restoration, you can choose which nodes in the cluster that you actually want to restore. When you go through the process of doing that recovery, it will prompt you for that that physical location or particularly what node you're looking to restore. You'll notice here that you can do the physical storage, which is an SFTP server. That's the option that you have to identify the backup, right? So the DRS, when you log into DRS for the first time and you're going in to perform a backup or you're doing a restore task, you have an interface for performing those functions, either backup or restore. There's a distributed system architecture that we have incorporated in the configuration for performing those backup and restore functions. You can do scheduled backups. You can also archive the backups to a remote SFTP server. You do not have the option of doing a backup to like a tape drive or some sort of storage location. All right. Now there are two main functions to the disaster recovery system. There's called what we call a master agent, and then there's something called a local agent. These are very important concepts when we're talking about the disaster recovery system. The master agent is what coordinates the actual backup and restore activity with the local agents. So the system, when it boots up and when it starts up, automatically starts the master agent on the publisher node, and then it starts the local agent on all of the cluster nodes within the call manager cluster. All right, so if you're running into an issue where the DRS system is not functioning, you may have to restart or kickstart those master agent and local agent functions, but you would only have to restart the master agent function on the publisher. All right. So what does the disaster recovery system actually back up and restore? It backs up the Cisco Unified Communications Manager database, the CCMDB, which includes the Unified Communications Manager, the call detailed records, analysis and reporting components, as well as the call detailed records. It backs up the platform itself. It backs up music on hold files. It backs up any kind of bulk provisioning services or bulk administration tool, bulk provisioning components. It backs up the CCM preference files. The TFTP phone device files get backed up as well. The SNMP syslog information gets backed up. The SNMP CDP sub-agent gets backed up. You don't have to worry about these specifically. These are all made components, and you can customize the backup to an extent, but most of this stuff is going to get backed up automatically, like the trace collection tool, cluster manager, Cisco extended functions, the reporter tool, and so on. These are all backed up. With IAM and presence, there's some other things that get backed up as well. The IAM and presence preference files, the presence database, the XMPP configuration files. We'll talk a little bit about XMPP later on. The IAM and presence configuration files, and so on. All right. Now, to back up and restore, or at least to back up the data to a remote device on the network, you have to have an SFTP server that is configured. Cisco allows you to use really any type of SFTP server product, but it recommends a product that has been certified by what we call a CTP, or a Cisco Trusted Technology Partner. GlobalScape is one of those certified products that works with Unified Communications Manager. I've found actually that most of the standard SFTP products do work, but GlobalScape is the one that's supported by Cisco. There are some other vendors that can be utilized, like OpenSSH, Cygwin, CYGWIN, Titan, but Cisco doesn't support like FreeFTPD, because FreeFTPD actually has a 1 GB file size limit on its SFTP product. There's some other restrictions. For example, for Cygwin to function properly as an SFTP server, you have to add a specific configuration element to the SSHD underscore config file, which is the ciphers AES 128-CBC and the Diffie-Hellman group exchange information. That information is documented in Cisco documentation. So just be aware that not every SFTP application is going to work specifically with the DRS system. Again, there are two major components: a master agent and a local agent. When the system boots up, it's going to automatically start the master agent on each node of the cluster. But the agent itself is only functional on the publisher. So that could be a little confusing. You can go into the subscriber nodes and you'll see a DRS master agent running on the subscriber nodes, but the master agent doesn't actually perform any particular function on those subscriber nodes. The local agent is enabled on each node within the cluster as well, including the node that actually contains the active master agent, but the node itself has to have an active local agent to do the backup and restore functions on that particular node. All right. By default, by the way, that local agent automatically gets started as well. So again, to log into the disaster recovery system, you're going to go to the navigation pane at the top right corner of the screen. You're going to click the drop down. You're going to go to disaster recovery system, and you're going to authenticate to that disaster recovery system. If it's an IMNP system, it's not called disaster recovery system. It's called the IM and Presence disaster recovery system, but it's basically the same navigation. All right. It is the same login. There are basically two different types of logins that exist with Unified Communications Manager. There's an OS administration login, or a command line login, which is set up separately than the call manager administration login. All right. When you do the initial setup of Unified Communications Manager, there's about, I don't know, don't quote me on this number, maybe 10 or 15 different questions that you have to go through. And one of those questions is what login or authentication do you want to use for call manager administration, and what login would you like to use for OS administration. Those values can be the same, but the DRS is the same login that you would use for the GUI administration or the call manager administration login. All right, you set up these administrative usernames and passwords during the installation. You can change that, during the process. You can change that, after the installation is complete. But there are two individual logins that get established. So that is really those are the details about the disaster recovery system. We have a question here. Which protocol could you use as part of the DRS? And SFTP is the only one that's permitted with the disaster recovery system. So that is the correct answer. So the next thing we're going to talk about is the dial plan. The dial plan, as it is with any phone system, is the most critical component to a phone system, right? The dial plan is a list of numbers that are either registered to the system or numbers that are identified within the system to allow external dialing from the system itself. And we can see from this diagram here that there are many dial plan components. Endpoint addressing, for example. All right, endpoint addressing is what we would typically refer to as our directory number architecture. Now, it doesn't have to be specifically a directory number. Endpoint addressing could also include something like a SIP endpoint identification pattern, which is not specifically a directory number, but it's a SIP qualified address. But anyway, the endpoint addressing component is how we identify the endpoints themselves. All right. So typically this would be a directory number or something, an extension or something that's assigned to the endpoint itself. Another component of the dial plan is manipulating the digits. Oftentimes when we're dialing numbers, we have to strip off digits. We have to change information about the pattern itself, either the calling number, the person that's doing the dialing, or the called number, the number that they dialed. And we can do digit manipulation within Unified Communications Manager in several different locations. We can do it on at the phone level. We can do it at the gateway level. We can do it at the route pattern level. And we'll see this a little bit later on as we get into more detail on how to set up the dial plan and configure the dial plan within Unified Communications Manager. But the whole point about the dial plan is how are calls going to be handled, what we call call treatment. Maybe it's I'm dialing a 9 as an access code to get out to the PSTN, but I want to strip that 9 off before I send the call to the PSTN so that the service providers know what I'm trying to dial. Or maybe I'm my caller ID only has my extension, and I want to expand that number to a fully qualified E.164 number so that if somebody sees the call on their end, they know that they know what the North American number is or the E.164 number is, which is a global specification for dial plan structure. I can manipulate the digits in that way, right? There are two major components when it comes to dealing with numbers. There's something called ANI, Automatic Number Identification, which is essentially caller ID. And then there's something called DNIS, D-N-I-S, Dial Number Identification Service. DNIS allows us to identify the number that was dialed. All right. So ANI is my caller information, and DNIS is what I dialed. Within Unified Communications Manager, we simply call it called number or calling number. So calling number is the ANI, and called number is the DNIS. In traditional PSTN terminology, you would see a reference to ANI and DNIS. In Unified Communications Manager, you see a reference to called number and calling number. There are many, many different places to do digit manipulation, and there is a specific order of operations when it comes to the digit manipulation. You can't just simply manipulate the digits at any point. One manipulation at one point might trump or override a manipulation at another point. So we'll talk more about that as we get into kind of the weeds or the details of dial plan configuration a little bit later on. All right. Another aspect of Unified Communications Manager that is extremely important is class of service or class of restriction. Class of restriction is typically a term that we would use to describe calling privileges in a iOS-based phone system like an SRST platform or a Call Manager Express platform. Class of service is what we would typically see referred to as the dial plan restrictions that are specified within Unified Communications Manager. But the idea of class of service or class of restriction is that we're restricting what a person is able to dial, right? Maybe you have employees that you don't want to have the capability of dialing international numbers, or you have employees that can only dial local numbers, or local long distance numbers, and so on. So calling privileges are a very important component to the dial plan itself. We are going to talk about this in much more detail a little bit later on in the terms of partitions and search spaces. Within the Unified Communications Manager, we use partitions and calling search spaces to define our class of restriction, to define our calling privileges. Now, think about it from this perspective, and I will mention this again later as we get into the dial plan details. A partition is a phone book, okay? So a partition is a phone book. Phone books contain numbers. So your directory number goes into a partition. A route pattern that you define within the system. A route pattern is a number that the system recognizes, and then it directs the call to a particular location, either a gateway or a trunk or whatever. Route patterns go into a phone book. So the partition is basically where the number is listed. A calling search space is a stack of phone books. So let's say, for example, I wanted to dial a number, and my phone was assigned to the XYZ calling search space. That means that I have that stack of phone books. And as long as the phone number is in one of those phone books, then I'm able to dial that number. If the phone number is not in one of those phone books, I'm not able to dial the number. All right, so that's how we do calling privilege restrictions within Unified Communications Manager. We use partitions and search spaces. There are basically only two things that go into a phone book: directory numbers and route patterns. All right, now there are some other concepts like translation patterns and transformation patterns and so on, but for the most part, it's really just route patterns and directory numbers. Those go into phone books, and then from those phone books, we're able to identify what we're able to dial and what we're not able to dial. So it's a very, very important concept. All right, we'll get into this in a lot more detail. Setting up the dial plan is extremely important. Setting up the dial plan is extremely important. All right. Other calling privileges can be done by setting up things like client matter codes. Although client matter codes don't really have anything to do with restricting the call, it allows us to at least identify the call. So let's say, for example, I'm a law office and I'm dialing a client. I can force the system to require me to enter a client matter code once I place that call, and then that client matter code is then going to be associated to that particular call. Okay. Now there is a forced authorization code. A forced authorization code would be like your typical, oh, you want to dial an international number? Well, we'll let you dial this international number as long as you put this passcode in, and then that passcode will define whether or not you're allowed to dial that number or not. So we'll talk about that as far as establishing calling privileges as well. Call coverage is important as well. Within Unified Communications Manager, I can have rollover extensions. I can say, okay, if this person doesn't answer the phone, do we send the call to voicemail? Do we send the call to a hunt pilot? And then the call rings multiple phones. What happens if the phone is not registered? How do I handle that call if the phone is not registered? Am I sending the call to a call handler within Unified Cisco Unity Connection? A call handler is basically a auto attendant, right? Press 1 for this, press 2 for that, press 3 for this. That's basically what a call handler is. We do that in Unified and in Cisco Unity Connection. Although now Call Manager does have some basic call handler functionality built into it. All right. So call coverage is what happens if the call doesn't get answered? What happens if the phone is not registered? What happens if I'm ringing into a hunt pilot and I'm broadcasting all the phones and nobody answers that call? How do I handle that call? All right. There's other call coverage functions, right? We can do group pickup, so somebody could pick up somebody else's call within a particular group and so on. All right. The other thing that's part of the dial plan is how do calls get routed? Okay. Now, the way that this basically works, let me just kind of break this down. We'll see this a little bit more later on as well. So the way that this basically works is you have a pattern, right? And maybe that pattern is, we'll just say 2 through 9. Well, let's do 9.2 through 9 XX 2 through 9 XX XXXX. There shouldn't be a slash there. All right, so that's a pattern. This is a let's do a 1 in there. This is an 11-digit dialing pattern, right? To do 11-digit dialing. When I set up that pattern, the pattern points to a gateway, which could be a PRI or a SIP trunk or a route list. Okay, so basically when we're talking about call routing and path selection, we're saying, okay, if somebody does dial this number, how is that call going to be routed in the system, right? A route list would point to a route group, and the route group would have a primary RG and a secondary RG. And inside of those, we would have, in the primary RG, I might have gateways or trunks. And in the secondary RG, I would have gateways or trunks. So again, it's basically, okay, if somebody dials this pattern, what are we going to do with that call? Are we going to send it to this SIP trunk? Are we going to send it to this PRI? Are we going to send it to this analog port, and so on? So when they say call routing and path selection, that's what they're talking about in this particular case. But we also have AAR, which is an automated alternate routing scenario. So maybe the call is supposed to route over the WAN because it's a site-to-site call, or maybe or it's something called THO. THO stands for tail end hop off. We'll talk about that a little bit later on. But the WAN is down, right? So the call can't be routed over the WAN. We'll use the PSTN, the public switch telephone network, as a backup. Of course, we have to do number expansion or manipulation in that particular case, because maybe somebody dialed a 4-digit extension, which works fine over the WAN, but the 4-digit extension doesn't work over the PSTN. All right, so when we say path selection, we're not only talking about what is the primary calling process and how are we routing the calls primarily, we're also talking about how do we route the calls secondarily if there's some alternate routing configurations set up. As I stated before we started this section here, the dial plan is the most important, well, really technically one of the most important components of a phone system, because the dial plan establishes the numbers. I mean, that's ideally what a phone system is designed to do. A phone system is designed to route calls. And so this is a pretty important concept when it comes to establishing the configuration. All right. We'll see more about this in more detail a little bit later on as we drill down into these configurations a little bit later on. So in this case, they want us to match the dial plan component on the left with its function on the right. All right, so endpoint addressing enables you to manipulate the dialed string. Let's do it the other way. Let's go from the right to the left. So enables you to manipulate the dialed string. That would be digit manipulation, right? So that one's going to go there. Enables you to access internal and external destinations. That would be call routing and path selection. All right. Enables you to deny access to certain destinations. That would be calling privileges. Enables you to use a secondary path when the primary path is unavailable. Let's see here. Maybe I missed something. Because endpoint addressing enables you to ensure that calls are not dropped without being answered. That's definitely call coverage. So something is not right here. Enables you to access internal, external destinations. I guess that would probably be endpoint addressing there, and then this one would be enables you to use a secondary path when the primary path is unavailable. Sorry about the messy lines there. So the only one that I changed here was this one right here, which is endpoint addressing. Enables you to access internal and external destinations, which is kind of a weird way of describing it, because basically they're saying, okay, in order for me to be able to place calls, I have to be a phone within the system. All right. To me, dialing internal and external destinations would be part of your dial plan, right? That's what allows you to do the dialing. But it makes sense that the other one is call routing. So we'll go with that. That seems to make sense. All right. So the next section we're going to talk about here is really just all of the protocols that are critical to the operation of any kind of unified communications system. Now, the goal of this class is not to learn how these protocols work or how they function, but the goal of this particular section is to describe why these protocols are important in a unified communications manager system. All right. So I'm not going to spend time talking about NTP and how it works and how we configure it and that kind of thing, but I will talk about its relevance to the configuration of Unified Communications Manager as well as the other UC systems on the platform itself. Now, generally speaking, NTP, the Network Time Protocol, is a time synchronization protocol. It runs over UDP port 123. It is something that we configure and set up when we install Unified Communications Manager for the first time. In fact, the UC installation will not proceed unless you can actually access an active NTP reference when you're doing the initial configuration and installation of Unified Communications Manager. So you actually have to specify an NTP reference when you're setting up the system for the first time, and that NTP reference has to be providing time. It's something that actually has to be functional. All right. If for some reason the NTP reference is not available, the installation will not proceed. So that's something that's pretty critical. Now, as far as what NTP is, right, as far as what it provides within the context of our UC system, it is kind of important, right? I mean, if you think about it, a lot of people, especially in a work environment, will actually rely on their phone to actually get time. And I cannot even count how many times I've gotten complaints from clients that say, hey, the clock on the phone doesn't match the clock on my iPhone or the clock on my computer or whatever. And surprisingly enough, people do rely on the time on their phone quite a lot. Now, you can specify up to 3 different NTP servers Typically they recommend obviously at least one internal reference and one external reference, but the publisher is the only server within the cluster that actually synchronizes from an external master clock source. All of the subscribers within the cluster get their time from the publisher. Now, why do I need accurate time within the system itself? Why is that important? Well, the phones themselves, like I said, display the date and time. And a lot of times, clients will rely on that information in order to tell what time it is. The phones themselves might have security features that are enabled, certificate-based authentication. There might be some sort of dial plan restrictions based on the time, because we can do time-based partitions and time-based calling restrictions. So the phone might allow a particular number to be dialed at this time of the day. Pretty typical when, like, say, international can only be dialed during business hours, and you're not allowed to dial international numbers after business hours or something like that. Additionally, all of the reporting records, the call management records and the call detailed reporting records, they're going to have timestamps, date and time information that are tied to them. Log files, trace files, troubleshooting, event correlation, those types of things require accurate time. All right. And again, there are some time of day routing functions. There are certificate-based security features. There are a lot of things within the system that rely on the time. Now, there are two places that you can set up the time within Unified Communications Manager. You can create something called a phone NTP reference, and that's done under the system parameters, and it's associated to the device pool. We'll talk more about what a device pool is a little bit later on. But the phone system, a phone NTP reference, is only going to be used for SIP endpoints, not skinny endpoints. There are basically two primary types of endpoints that exist within Call Manager. Skinny, what we call SCCP, or Cisco Client Control Protocol, or Skinny Cisco Client Control Protocol endpoints, and then we have SIP endpoints, Session Initiation Protocol endpoints. The phone NTP reference is only for SIP endpoints. And then you have an NTP reference in OS administration. That would be the NTP reference that you set up when you're installing the operating system for the first time. That's the reference that the entire server is going to use. So you can go into OS administration and you can modify that configuration and so on. All right. So that's something that definitely needs to be established and configured when you're configuring the system for the first time. Another protocol that's important is DHCP. We understand generally what the purpose of DHCP is, the Dynamic Host Configuration Protocol. Obviously, we're going to assign an IP address to an endpoint. We're going to assign a subnet mask, a gateway. And those are important components for our endpoints, right? Our phones typically, which use DHCP. But we also might be assigning DNS information. But perhaps one of the most important aspects of the DHCP element is to assign something called a TFTP server address. Cisco phones utilize a protocol, Trivial File Transfer Protocol. We'll talk about that in a minute, but the phones use TFTP to obtain their configuration information from the Call Manager cluster. So when a phone boots up and it initializes for the first time, which we'll talk about in the next module, but when a phone boots up and it initializes for the first time, it looks for an XML configuration file, either a default XML configuration file for that phone type, or it looks for an XML configuration file that is specific to that particular endpoint based on the endpoint's MAC address. That XML configuration file is how the phone is supposed to configure itself. So we get that information from TFTP. Now, there are a couple of options when we're using TFTP. There's a Cisco proprietary TFTP option called option 150, and then there's an open standard TFTP option called option 66. Either one of those will work when you're establishing the TFTP information. The format of the TFTP option is typically an IP address, so we're going to specify the IP address of the server within the cluster that's running the TFTP service. All right, not every server in the cluster has to run TFTP. Any node can be configured to run TFTP. Doesn't have to be a publisher, it doesn't have to be a subscriber, but at least one node within the cluster has to provide those TFTP services. That's very important. All right. Now you can establish the server DHCP configuration on the call manager cluster. It's not recommended, particularly in a large-scale deployment. There are resource limitations to running DHCP on the call manager servers themselves, but DHCP is a service that you can run on the call manager server. So if we take a look at this Visio diagram, you'll notice here that one of the things we see is the DHCP monitor service. What happened to my mouse? There it is. The DHCP monitor service. That is a service that I can enable on the server, and then I can specify the DHCP configurations. So if I have the DHCP monitor service plus the DHCP configurations configured on the server, it can act as a DHCP server for the cluster itself. But that is an option, right? It's not a requirement. We typically could run, we could run DHCP anywhere in the enterprise, right? Now keep in mind, DHCP uses UDP port 68 and 69, or 67 and 68, excuse me. And it is a broadcast-based protocol, so obviously you're going to have IP helper or some way of propagating that DHCP information to the DHCP server. But obviously we want to assign addresses to our phones. We want to be able to have them join the appropriate subnet and so on. All right, so what are some of the common problems with DHCP? Maybe the server is down. Maybe the phone is not in a common subnet with the DHCP server, so the broadcast traffic is being blocked because I don't have the appropriate IP helper address configured. Maybe all the addresses in the scope are used up and there are no more leases available, or maybe the DHCP server doesn't have the appropriate parameters established. Maybe it's not running option 150 or option 66 to assign the TFTP information to the phones themselves. All right. So DHCP, even though it's not maybe specific to Call Manager, even though it can run it on Call Manager, is certainly a protocol that's going to be used within the overall context of the architecture. All right. DNS is another protocol that can be used. The general guideline, all right, for the general guideline for most implementations is to try to reduce the reliance of DNS within your architecture. If you're using, advanced SIP features and SIP dial plans and whatnot with SIP URIs, DNS might be required. But if you're using just standard dialing functionality, DNS is not necessarily required. So when you're establishing the system configuration for the first time, you may, most of the references for the service button on the phone to reference different services from the phone will rely on DNS. But you can take that out, and we'll actually see that in some of the advanced configurations that we take a look at a little bit later on. We understand what the overall protocol is, right? It's, again, a UDP/TCP based protocol, runs over port 53, and it's used for resolving human readable names to an IP address. The reason we may want to eliminate the need for DNS is it's just another point of failure or point of possible failure in the overall operation of our phone system. I mean, if you think about it, traditional phone systems didn't use DNS, right? Which makes sense. I mean, traditional phone systems were just traditional phone systems. They didn't really have any kind of IP connectivity. So if we can configure out the reliance of DNS and use IP addresses only, then that will eliminate that possible single point of failure. Of course, using DNS provides the benefit of using names instead of numbers. So if the numbers change but the names do not, it makes it easy for us to kind of reference those numeric changes based on the fact that we're using the same DNS name. All right, but if DNS is unavailable, that can cause a problem. All right. The amount of time that it requires for a device to perform its function can be shortened if we're not using DNS, because it takes time to do the DNS query, it takes time to get a resolution and get a reply, and so on, especially if you have kind of a nested DNS architecture and you're doing zone transfers and stuff like that. So it is, you know, there are kind of two different points of thought here. If you look at the advantages versus the disadvantages, you have to make a decision as to what benefits you the most in your environment based on how you're configuring your environment and how you're managing that. And then you can make a decision as to whether or not you want to allow DNS or not in your configuration. All right. TFTP, UDP-based protocol that works over port 69. A very, very simple file transfer protocol. Again, TFTP is essentially how the phones get their configuration, but there are some other things that are provided by the TFTP service. All right. The TFTP service provides the phone configuration through an XML configuration protocol. The phone firmware files are provided through TFTP as well. So the firmware is the software that gets installed on the phone itself, and that is the essentially the operating system of the phone. Now, the firmware is typically tied to the version of Unified Communications Manager. So if you're running 10.x, you're going to have a specific firmware file for an 8900 series phone. But if you upgrade to 12.x, the firmware for that particular 8900 series phone will most likely get upgraded as well. Now, we can manage those firmware files system-wide, or we can manage those firmware files on a per-device basis. We'll get into that a little bit later on in the next section, actually. But the process of installing or downloading that firmware and putting that firmware on the phone is the responsibility of TFTP. The CTLs, we talked about that previously in this section, the certificate trust list and the identity trust list files are going to be requested, and the TFTP configuration is going to allow us to access that information and then also verify that signature and verify that the configurations that we're getting over TFTP come from a trusted source. The network and user localization files. Localization is a term that we use to describe how the phone system is going to interact with the end user. What kind of cadence do I have in the ringtones and the ringbacks? You know, if you're in the United Kingdom, the phones sound different than if you're in the United States or if you're somewhere else in the globe. Not everybody uses the same ringback tones. A ringback tone is what you hear in your ear when you're dialing a phone number and it's ringing back to indicate that the call is proceeding. So we have different ringback tones, we have different enunciator messages, we have different basically what we call tones and cadence, country-specific tones and cadence. Not to mention languages themselves, right? If I'm in Germany, I don't want necessarily the information displayed on my screen to be in English. I might want the information on my screen to be displayed in German. So localization files are also provisioned and processed through TFTP. Ringtones themselves, these phones can support multiple ringtones. We're going to download those through TFTP. Soft key files. Soft keys are the buttons on the phone, right? There's line buttons, and then there are soft key buttons. The line buttons are typically on the vertical axis. Those are the buttons to the side of the display, and then the soft key buttons are on the horizontal axis below the display. Those are the kind of rectangular buttons that you see below the display. Well, not every phone has rectangular buttons, but you get the idea. The soft key buttons are the function buttons that exist on the phone. So if you're on hook, is there a redial soft key? Is there a new call soft key? Is there a do not disturb soft key? When you're off hook, is there an end call soft key? Is there a transfer soft key? That kind of thing, right? So those soft key files are going to get downloaded through TFTP as well. And if you're running SIP phones with local dial rules, where the dial plan gets downloaded to the phone, we're going to use TFTP for that as well. All right? Now, if the phone doesn't receive its configuration from TFTP, there could be a couple of different options. Maybe the DHCP scope doesn't include option 150 or option 66. Maybe option 150 is entered incorrectly and it's pointing to the wrong address. Or maybe the TFTP service is not running on the platform, right? On this Visio diagram, you can see all these circular references. Anything that's a circle here is referenced as a service. And TFTP is a service that can run. I don't know if I actually have that one listed on here. I think I only put the services that were critical for other functions to work. Yeah, so if you're going to be a call manager publisher, you have to have these services running. If you're going to be a DHCP server, you have to have this service running. If you're going to act as a call agent, you have to have that service running. So I don't think I put TFTP. If you're going to run these media resources, you have to have IP voice media streaming service running. But TFTP is a service that that you can run as well. It's what we call a feature service. In Unified Communications Manager, there are two types of services that exist. There are feature services and there are network services. Feature services are services that are optional. You can disable them, you can enable them, you can restart them, you can stop them and start them, and so on. Network services are system critical services. These are services that have to run on the node in order for it to function. So network services get installed and turned on when you install the operating system. And you don't have an option to disable network services. You do have an option to restart them, but you don't have an option to disable them. We'll see that a little bit later on when we get into the service configuration component. All right. Some of the newer phones don't use TFTP. They'll actually use HTTP using port number 6970 or HTTPS using port 6971 and 6972. TFTP is kind of a legacy protocol. It's a little bit slower than HTTP. All right. Now another important protocol, very important protocol, is the Cisco Discovery Protocol, or the open standard version, the Link Layer Discovery Protocol with the extensions. All right. The purpose of CDP. CDP is a Cisco proprietary protocol, works at layer 2. You can see here when the phone boots up, the first thing that it does once it receives power and the phone boots up, the first thing that it does is it tries to discover what VLAN it belongs to. Now, if it's a Cisco phone and a Cisco switch, no problem. We can use CDP to do that. So the phone will send a CDP message. It will identify itself as a phone. The switch will say, okay, you're a phone. You exist in this VLAN. On that switch port, we have the data VLAN configured, and then we have the auxiliary VLAN configured, which is what we call the voice VLAN. And we would actually do that complete that configuration by going into the switch and saying switch port voice VLAN 100 or whatever the VLAN is. All right. That voice VLAN is the VLAN that the phone belongs to. So before the phone can do a DHCP discover and get its IP address information and identify what subnet it belongs to and then get its TFTP information to download its configuration, it needs to know what VLAN it belongs to. And CDP is the way that we do that. We use the Cisco Discovery Protocol to discover the VLAN. Now, what if we're connecting a phone to a switch that doesn't support CDP? Maybe we're using some sort of substandard Juniper switch or HP switch or something like that, although HP does support CDP. Then we need to have a, if I have a switch that doesn't support CDP, then I have to use LLDP. Now we could spend a couple of hours talking about the differences between CDP and LLDP, but generally speaking, they're basically the same thing. They allow us at the data link layer to discover directly connected devices. So we'll identify what type of device it is, what its basic functionality is, what its capabilities are, and some auxiliary information can be gleaned from the process of this discovery. But again, the whole purpose of these protocols in this particular case is to be able to identify what VLAN the phone is in so that it can continue with its registration process. It's a little bit beyond the scope of this class to go through the protocols specifically and identify how the protocols function. All right. Now LDAP, we're actually going to have a discussion of LDAP in our next section here, and we're going to talk specifically about how LDAP works and what its particular function is. It plays a pretty significant role in most modern implementations of Unified Communications Manager. LDAP as a protocol is just a directory protocol. It allows us to collect and parse and access information in a directory structure for username information. And it can contain things like username, password, department, phone number, email. Basically, it's a directory of the users in the system. Now, LDAP isn't incorporated into the platform directly, but there is a way for us to synchronize to an external LDAP database through Active Directory or some other directory service. All right. The idea here is that we have a single location for us to store our user information, and we can synchronize that user information from that central repository. All right. Rather than having to manage separate users in Call Manager and separate users in Active Directory and separate users in Unity Connection and separate users in UCCX, we can synchronize to the centralized database for the purposes of just synchronizing the users or for the purposes of authentication. All right, so there's actually two ways that you can implement LDAP within the UC system, and we'll definitely get into this in a lot more detail later on. But if you look here, we have the ability to synchronize to the directory if our whole goal is just to synchronize our users to the LDAP directory, but we also have the ability to use LDAP integration for authentication as well. And I'll get into that in more detail a little bit later on. But when I'm configuring LDAP, if I'm just using LDAP to synchronize the information, I'll use the authentication credentials within Call Manager as the authentication credentials. If I'm using LDAP for authentication as well as synchronization, I'll use the credentials that are stored in LDAP for the authentication itself. There are lots and lots of different types of directory services available. Microsoft Active Directory is probably the most popular. You also have Open LDAP and so on. Another protocol that's important for the implementation, although it's not mandatory, is SNMP, the Simple Network Management Protocol. All right, SNMP, application layer protocol, to be able to manage really any kind of system. right? We have these things called MIBs, a management information base, which is essentially a directory or a structure of the managed device. You know, its basic management architecture, if you will. We have the network management station, which is essentially the network management platform that's managing the systems themselves, which can be HP OpenView, Boole and Babbage, SolarWinds, Cisco Prime LAN Management Solution, and so on. Pretty much any SNMP platform can act as an NMS. SNMP is an open standard protocol. All right. So as you can see from the diagram here, we have the ability to run SNMP on Call Manager, and we can get traps or informs from Call Manager if an event occurs, a phone doesn't register, a resource is not available, whatever it might be. Depending on the MIBs themselves, will depend on what we can actually gather, the type of information we can gather from the system. And we can also set information. So I can push configurations through SNMP to the platform as well. All right. So the managed node is the device that we are managing, and then the agent is the actual daemon, if you will, or software that's running on the managed node that provides us the ability to run this protocol. Okay. And Call Manager supports SNMP 3, SNMP v2 and v2c, SNMP v1, and so on. Although I recommend using SNMP v3 for its cryptographic features, right? The security features. All right, which protocol is an extension of a classic LLDP that enhances the support for voice endpoints? That is the MED component. Again, the MED component adds these containers, we call them type, length, and value fields, that allows us to have the necessary enhanced features, for managing the phone itself, specifically being able to identify the VLAN that the phone belongs to. There's definitely some other components to it, and again, it's a little bit beyond the scope of this class to get into those specifics because we have a lot of information to cover, but the MED extension is what allows that support for the voice endpoint. All right, in discovery number 2, we're going to talk about configuring IP network protocols. When we implement a unified communications architecture, there are lots and lots of different protocols that we need to implement in this collaboration environment in order for the environment to function as we need. Some of the common protocols that we'll see are NTP, our network time protocol, DHCP, the dynamic host configuration protocol, DNS, domain name service, TFTP, the trivial file transfer protocol, Cisco discovery protocol, LLDP MED, the lightweight directory access protocol, and the simple network management protocol. There's certainly other protocols that we have, but these are most of the IP-based network protocols that we're going to need in order to facilitate our topology and our configuration. In this topology, we have 2 different IP communicators. We have CIPC1 on PC number 1. We have CIPC2 on PC number 2. Those are my IP communicators, or my soft phones. This overall topology kind of represents our topology for the network. The 10.1.5 subnet is what we're using for the basic connectivity between all of our devices. We do have a Windows server that's not depicted here, and that Windows server is acting as our NTP server as well as our DNS server. We also have a CSR router, but this CSR router is configured as the gateway. It's going to be used to access other networks within the lab environment, but we're not going to be doing any configurations on that particular router. We're also going to configure DHCP on the Call Manager server, which has an address of 10.1.5.5. PC2 is going to be a DHCP client in this particular case, and we're actually going to look at Wireshark on that device to verify the DHCP DORA process and the operation of DHCP. We're also going to configure and verify DNS, A records, Quad A records, PTR records, and SRV records. And then we're going to configure NTP to allow router number 1 to act as an NTP master. and then use NTP from the Windows server as its particular time source. The last thing we're going to do is we're going to configure Call Manager to synchronize its time to the NTP server, and we'll get into troubleshooting some of the common problems that we see in this environment with these different applications. We're also going to come over here and configure this switch. Port 1 and port 2 have a couple of phones attached. We're going to take a look at CDP as well as LLDP on that switch. We're not actually going to physically use these phones in our topology. We're only using the soft phones in our topology, but these phones will provide us the ability to kind of identify how CDP and LLDP are functioning within our environment to be able to identify those phones. All right, some of the commands that we're going to use in this show NTP status, show NTP associations, NTP master, NTP server IP address, LLDP run, LLDP receive and transmit, show LLDP neighbors, show LLDP entry, and so on. We'll be using these commands throughout the discovery. All right, so the first thing we're going to do is we're going to go into PC number 1. We need to go ahead and authenticate here. And we're going to log into these PCs again for the purpose of utilizing IP communicator on these PCs. So our first task is to go ahead and make sure that IP communicator will register. We also want to make sure that it changes from a skinny phone, a Cisco Client Control Protocol phone, to a SIP phone. So let's go ahead and launch our IP communicator application. This is a soft phone application. We're really kind of using it in this particular environment to basically simulate a physical phone. These soft phones are not typically used too often in an enterprise environment, but we are going to use it here because we're running a virtual environment. When the device is provisioned, when a CIPC device is provisioned in Call Manager, you reference it by the device name, which can be the MAC address of the network interface that's tied to the CIPC server or to the CIPC application, or we can actually use a custom name. And these are the names that are actually specified within Unified Communications Manager. So this soft phone should reboot and it should register with an extension of 11,001 and the user is John. All right, so we'll give that a second to boot up. We're going to do the same thing on PC number 2. In the case of PC number 2, PC number 2 is going to be extension 11,002. So let's go ahead and authenticate. And CLL at B. And we're going to do the same thing on this phone as well. We'll go into our IP communicator and we're going to specify that this device is CIPC number 2. All right. Right click, go to our preferences, go to network, and document this as CIPC. We'll see the phones provisioned in Call Manager in a little bit as well. All right. All right, so let's take a look at PC number 1 and see if our phone has registered. It hasn't registered just yet. Let me go ahead and reset it and see if that will help with this process of registration. All right, this phone is rebooting as well. So I had to give the phone the right name. I actually put in CIPC there, so I'll go ahead and I went ahead and fixed that. The phone is downloading an update and it is now registering. So we can see the phone resetting. It's going through the process of registering, and finally we have an extension. It's going to reboot one more time, and we should see that extension pop back up, and I should get some dial tone when I press the line button. All right, so we have connectivity there. Let's go ahead and check the other PC as well. Looks like this communicator is still booting up. We'll give that a second to boot up. We may have to kind of kickstart it as well as part of the process. All right, so it looks like it's downloading some software. So we'll let that run in the background. Our next task once we've verified that the two devices have booted up, is to go ahead and configure DHCP. DHCP runs on a secondary protocol called BootP. And there are two components of BootP, BootPC and BootPS, which provide a framework for passing this TCP/IP configuration information to the devices. All right, a little bit of a delay there on the dial tone. So we're going to configure and verify DHCP on our call manager server. Now, just to kind of give you some information, DHCP as a protocol simply allows us to receive network configuration information. And it uses a process called the DORA process, which is a DHCP discover, an offer, a request, and an acknowledgement. We're going to take a look at that in Wireshark in a little bit as part of our configuration process. And I'll show you guys what those Wireshark captures look like. DHCP is a broadcast-based protocol. At least the initial DHCP discover is broadcast. And depending on whether the client has actually received an address in the past or not, will determine if any of the remaining transactions are going to be unicast or broadcast-based. All right. So the first thing they want us to do is go into PC number 2. All right, let's go over to PC 2. We can see that it's booted up here. Got a little bit of a delay on the dial tone for some reason, not sure why. But let's go ahead and go into our control panel, and we're going to switch this device to DHCP. All right, so we'll go over to Network and Sharing Center, and then we're going to go to Change Adapter Settings. And right now this PC has a static IP address. Oops, don't want to diagnose the interface, sorry about that. We'll go to Properties, and under TCP/IP we can see that we actually have a static IP address. So we're going to go ahead and just switch this to a DHCP address. Not quite yet, right? We still have to go in and configure DHCP on the Unified Communications Manager. But I just wanted to show you that we presently have a static IP address on this particular device. And there's my dial tone from my previous, when I pushed the button previously. Interesting. Again, this is virtual equipment. Well, it's physical equipment in a virtual location, so I'm not sure why we're getting that delay in the dial tone. But let's go ahead and continue on. So we're going to first go into Call Manager Administration. We'll come back to PC number 1, and we're going to open up our browser, and we're going to go to the Call Manager IP address. 10.1, oops, 10.1.5.5, and it should automatically redirect us to the Call Manager application page. We'll go ahead and accept the self-signed certificate in this particular case, and this is our Call Manager login. So we're going to log in as administrator. This is our application user that we created when we installed Call Manager originally. Administrator and C0LL at, oops, C0LL L at B. That should be the login. All right. So once we get logged into Unified Communications Manager, before we actually get into configuring the DHCP, let's go ahead and make sure that our phones are registered. Well, we know they're registered, but I want to show you what they look like in the list here. And what we're looking at specifically is that CIPC1 and CIPC2 are in fact registered. And we can see the IP address that they are using, which is basically just the IP address that is borrowed from the network interface card on the PC itself. The status is registered, they're running as SIP phones, they're attached to this call manager, and this is the description for those devices. I can also go into this IP address, and I can actually take a look at, let me turn off my annotation tool here. I can actually take a look at specific phone information for that phone. There's the DN, that's the software version. If I was on an active stream, I would be able to see active information about that stream on there as well. RTP, or basically reported RTCP information specifically for that particular device. All right, so we know that the phones are registered, we know what IP address they're using, and what I want to do now is I want to go ahead and close out unified the CIPC application on PC number 2. So let's go into PC number 2, and we're just going to simply kill this this IP communicator that's running on this PC. So let's close all that out, and we're going to right click. If I just click the X here, it's just going to minimize the application. So I just want to right click and click exit to actually remove that or disconnect that phone. And I should see the status of that phone change. Let me just go back to device and phone and click find, and I can see that the device is now unregistered in the system. Really straightforward. I mean, it's real-time information that we're getting from the device as it's participating. So the next step is to go ahead and set up our DHCP server. So we're going to go to System, and we're going to go to DHCP, and then specifically DHCP Server. All right, we're going to add a new DHCP server in this particular case. The host that we're going to be running this on is going to be our call manager, and the starting IP address, or the primary DNS IP address, is going to be 10.1.5.100. That's our Active Directory server. Option 150 is going to be our call manager server. We can specify multiple addresses with option 150. Option 66 doesn't support that, but that's okay. We're not using option 66. Remember, option 66 is the open standard version that provides us the ability to assign a TFTP address in a DHCP configuration. So we'll go ahead and save that configuration. We're also going to now go to System, and we're going to go to DHCP. We're now going to create our scope. All right, we don't presently have any scopes defined, so we're going to add a new scope, and that's going to be based on the DHCP server that we just implemented. And we're going to specify that the subnet address is 10.1.5.0. The starting address is going to be 10.1.5.210, and the ending address is 10.1.5.220. Our primary gateway, our primary router IP address is 10.1.5.254, and the subnet mask is 255.255.255.0. DNS that we're going to assign to the clients is 10.1.5.100. And then we also want to make sure that we assign the primary TFTP address in this particular case as well. So we're going to come in, go down to the primary or the TFTP address, and we're going to specify 10.1.5.5. So let me scroll down here. The TFTP server, well, this is an option 150. We can use option 66, but there's really no reason in a Cisco environment not to use the Cisco supported TFTP option. Option 66, as you can see here, doesn't provide us the ability to specify a primary and secondary TFTP server, but with option 150 we can. All right, so we're going to go ahead and save that configuration. Now we're going to go back to PC2. We're going to open up our Wireshark application, and we're going to specifically look for bootp information. All right, we'll capture on Ethernet 0, and we're going to filter this based on bootp traffic. We could do other filters, right? We could filter on port numbers and so on, but in this case, we're going to filter on bootp traffic. So now I'm going to go back to my desktop here, and oops, I'm going to go back to my desktop here. I minimized the wrong window there. Go back to my desktop and go back into my network and sharing center, change adapter settings, and I'm going to go back to my Ethernet port, and we're going to just switch this Ethernet port to DHCP. So we'll come over to TCP/IP, obtain an IP address, obtain DNS through DHCP. All right. And what I should see then in that Wireshark capture is I should see that information about, the Wireshark information about boot P. Let's make sure I change the right computer. I did not, so let me go ahead and fix that. We want to make sure that we do PC number 2. All right, so let's go over to PC number 2 this time, and we're going to do this on PC number 2. All right, let's skip that. Go to our Network and Sharing Center, go to our Change Adapter Settings, go into the properties for our network adapter, and again, we're going to disable static IP and enable DHCP on this particular device. Now, of course, as soon as this happens, the client is going to now start sending out a discover message. And we can see that in this particular case. Let me go ahead and scroll up here. So we can see the DHCP discover, the offer message, the request, and the acknowledgement. All right, indicating that we're going through the process of, we're going through the standard DHCP process. If I were to drill down into the discover, we can look at the layer 2 information. The source MAC address is the basically the interface MAC address. The destination MAC address is a broadcast. It is an IP packet. DHCP is an application layer protocol that's transported inside of IP. We can see that the protocol, the transport layer protocol is UDP, but notice the source and destination IP. The source address is quad 0, the destination address is all 1. So this is our DHCP discover message. If I drill down to the UDP component, I can see that the source port is boot PC, which is 68, UDP port 68, and the destination port is boot PS, which is UDP port 67. And then I can go into the DHCP payload information, and I can actually see that this is in fact a discover. Here is the discover, and we're identifying this within option 53 as a discover. We're also providing client ID information for this client. So if there is already a leased address or some reserved address for this client, or even a static configuration, we're able to identify that. We're also identifying the host name of the device, so we can do some dynamic DNS stuff if we need to. And then these are the parameters that we're requesting, right? We're requesting the subnet mask, the router, DNS, domain name, the static route, which will most likely just be a default route, and some other information, all right? Now, if I look at the offer is coming from the DHCP server. Pretty much everything at layer 2 and layer 3 is going to be the same, with the exception of specific IP addresses. But now the source is boot PS, and the destination is boot PC, because it's coming from the server and going to the client. But if we can go look at what is being actually offered in this process, we're providing a mask, we're providing a lease time, we're actually identifying who the DHCP server is in this case, which is our call manager server. And we can see the default router. But one thing that we're looking for specifically is option 150. And we should see option 150 in here. Let's see, where is that at? Well, we don't actually see it in here. I see option 51, option 54, 53, but I'm not seeing the option 150. Let's see if option 150 gets presented in the final acknowledgement message. Well, let's actually check this offer. This might have been a previous configuration. It looks like, in fact, it was, because we look at the address here and we look at the address here, and they're different. So maybe we see our option 150 in this offer here. All right. Let's see, option 255, 6, 3, 1, 51, 54, and 53. So that's kind of interesting. We're not getting an option 150, but it should definitely be part of the scope. Let me take a look at the final acknowledgement as well, because in the final acknowledgement, I should be acknowledging all the options that I'm receiving as well. So that's interesting. Let's see if maybe Wireshark is just not reporting that. Certainly the IP phone should boot up and it should register based on the new IP address information. But let's see what we see here. It could be in this particular case, because it is a PC running a soft phone, that option 150 is not going to be something that's going to be accepted by the PC. Right? Now, if this was a physical phone, we may be requesting in our original DHCP Discover, we might actually request to be provided 150 information. But in this particular case, I doubt the PC, because PCs don't really work with TFTP, I doubt that the PC is actually even requesting option 150 in the option list in the original Discover. Let's take a look at that and see. All right, so scroll up here and let's go to original Discover. And if I look, I can see specifically what the PC is requesting as far as parameters go. And we can see it's requesting 53, 61, 12, 60, 55, and that's it. So that's why we're not seeing option 150 being presented, because the PC is not requesting that directly. All right. It didn't affect us as far as our operation of our soft phone, because we have option 150 configured in the soft phone directly. So let's go back to PC number 1. We'll go back to our call manager application, 10.1.5.5. And we should see, if I go to device and phone, I should see the phone is registered, and now it's using address 211. So it is definitely using the address that we had specified in within the DHCP scope, what falls within that DHCP scope. Now, I would say that it's probably not necessarily best practice to implement DHCP on the call manager server. There are some limitations to running DHCP on the call manager server with regard to how many endpoints it will support. But for a small office or a branch office, it works fairly well. You know, we're somewhat limited in what we can define within the scope, but we would normally use DHCP from the call manager server only to facilitate the connectivity of our voice endpoints, not our data endpoints. All right. So now let's go ahead and place a call from PC1 to PC2. We're going to just go ahead and seize the line here. And actually, let's just do it from this side. We'll just dial 11002 in this case. So the call is proceeding. We get that delay in audio for some reason. I'm not sure why, but the call is definitely proceeding. All right, so that audio will probably pop up here any second. All right, so the phones are registered, they've booted up, no problem. The next task is to go ahead and take a look at DNS. DNS is a distributed database where we can map human readable names into IP addresses through that DNS protocol on the DNS server. All right, each unique IP address has basically a host name that it gets tied to. So we're going to configure DNS on our Windows server to resolve our A records and our quad A records. A records are used for IPv4, quad A records are used for IPv6 on our call manager. We're actually going to create a server record. We're not going to use it, but we can create the server record for, say, example, for an XMPP client service that points to the CMS server, cms.cll-collab.internal.host. Again, we're not using it in this particular topology. Resource records are what are used inside of DNS within the DNS zone. And there are different types of resource records that are available in DNS. A records are the kind of the primary records that we use to kind of represent the host name to IP binding. Quad A records, similar thing for IPv6. A pointer record or PTR record is a record that allows us to resolve the IP address to the domain name, but unlike an A record, which points the domain name to an IP address, It's basically the reverse, or what we would refer to as a reverse DNS lookup. So we can specify that as well. A service record, or SRV record, allows basically us to identify within DNS host names and port numbers of servers that are providing specific types of services. This is going to be defined actually in RFC 2782, and it has a type code of 33. We don't really need to get into the specifics of a server record, but it really just points to a specific host and port for specific services, and it's actually used over voice over IP networks for things like instant messaging and so on. All right, it provides us basically that symbolic name and the transport protocol that is used as part of the domain name to provide those services. Now, although the main purpose of DNS is to point domain names to IP addresses, we have all of these other other records, if you will, that provide us the ability to provide these other services within the DNS architecture. So on PC number 1, we're going to go ahead and open up a command prompt, and we're going to go ahead and do an NS lookup for specific destinations. All right, so let's go into our command prompt, and we're going to do a NS lookup, which is a tool that allows us to do DNS queries, and specifically we're going to look up Cisco.com. So www.cisco.com, and we get a response, win-server1 cll-collab.internal. We can see we're running IPv6. There's a global unicast address. That's the one that starts with 2600. That's our quad A record. And we have our A record of 104. And then we can see all of our C names, or our aliases, for that particular domain. All right. Now, if I want to go ahead and verify the CUCM publisher, I can go ahead and put in the CUCM publisher name, CUCM, CUCM-pub.cll.collab.internal. Oops. All right, and we can see that that resolves to win server 01, but it can't find specifically CUCM-pub. All right, it doesn't resolve to win server. That's our DNS server that it's actually looking at, for the information on. We can also check the by IP address to see if we have a pointer record, and 10.1.5.100. Oops, 10.1.5.100 is our server, our Win server, and if I go ahead and try to find 10.1.5.5, we can see that we don't have an entry in the domain for that. So the next thing we want to do is we want to go ahead and remote desktop to our Windows server from this PC. We don't have any console access directly to that server. So we're going to go into our remote desktop application. All right, and we're going to connect to 10.1.5.100, 10.1.5.100. Administrator and C0LL at B. Yes. All right, so what we're going to do on a Windows server is we're going to open up our DNS settings, and we're going to go into our forward lookup zones, and specifically we're going to look at the CLL-collab.internal zone. All right, so let's go ahead and go into DNS here. We're going to go to our forward lookup zones, and specifically CLL-collab.internal. For the A record and the pointer record and the SRV records, we see there are lots and lots of different records that are configured here, a lot for different virtual machines and devices. We have a record for access-VM2. all right? And that's going to resolve to 10.1.5.201. But there is no record for CUCM pub. We have one for CUCX pub and CUCM sub, but we don't have a record for CUCM pub. All right, so we're going to go ahead and right-click the domain, and we're going to go ahead and create a new A record or host record, and then we're going to put in that information. The name is going to be CUCM-pub, and the IP address is going to be 10.1.5.5, and that's going to fall in the CUCM pub CLL-collab.internal domain. All right, so we'll go ahead and add that host. If I wanted to do a v6 entry, then I would simply go ahead and put in the v6 information. So now I can see if I close this out and I refresh the information here, I should see CUCM pub listed. Oh, well, dang it. I typed it wrong, so let's go ahead and change the properties here. That's why it wasn't listed in the right order. CUCM. Obviously, make sure that you put the information in correctly. I'm probably going to have to delete it and re-add it. So let's go ahead and do that. Let's go ahead and delete this entry and re-add the entry. Make sure, of course, that you type things correctly. CUCM-pub, and that's going to have an address of 10.1.5.5. All right. Now it will show up in the list right above CUCM sub. Let me go ahead and kind of refresh this, and we see CUCM pub listed there now. All right, and that is the A record. All right. Now we want to go to the reverse lookup zone, and we want to add our pointer record for the same domain. All right, so we're actually going to go into the reverse lookup zone, and it's going to be 5.1.10, which kind of represents, if you will, the reverse of the domain. And we're going to add a new pointer record, and here we're going to put in 10.1.5.5, and the host name, the fully qualified domain name shows up there, and we're going to put in the host name of CUCM-pub.cll-collab.internal. All right. Now, oftentimes when we're actually setting up Unified Communications Manager, a lot of times what we will do is we'll try to kind of reduce the reliance on DNS within the environment, because it's just another kind of point of possible failure within the environment. But in this case, we're just trying to demonstrate that we're actually able to set this up, and we can use our DNS server to provide this information. All right, so let's do a CUCM-pub.cll-collab.internal. And that should actually resolve CUCM pub. Oh, see, I misspelled it again. There's a little bit of a delay in typing here, so we're kind of getting that delay. CUCM-pub.cll-collab.internal. I spelled internal wrong. All right. Good thing I didn't go to school for typing. All right, so the address is getting resolved to 10.1.5.5. I can also check the pointer record by simply typing in 10.1.5.5, and I can see that gets resolved to CUCM pub CLL-collab.internal. All right, now let's go back to PC number 2. We're going to go into our Wireshark application, and we're going to filter based on DNS information. All right, so let's close out this individual capture, and let's go and close out this individual capture. Well, let's just actually do a search for DNS. All right, So the next thing is they want us to go ahead and open up a browser, and they want us to browse to the fully qualified domain name. So I'm going to come into my browser and I'm going to just type in the name instead of the IP address, https cucm-pub.cll-collab.internal. All right, and that resolved. And we can go ahead and accept the self-signed certificate, and we get access to our Call Manager administration page. All right, so now if I go back to Wireshark, I should see that resolution taking place. All right, right here, well, actually right here, let's scroll down, or scroll up, excuse me, and we're looking for the A record right there. All right, so we received the query for CUCM pub CLL-collab.internal, and then this is the response for that resolution, and it's telling us that the IP address is 10.1.5.5, which is what we would expect to see. Okay, all right. We could also flush the DNS if for some reason the information was already cached. We could go in and flush the DNS information and take a look at it again. All right, now we're going to go back to our server. So let's go back here. Actually, it was on PC2, was how we were accessing that information. We'll minimize Wireshark. And let's go back to our remote desktop connection. Maybe that was on PC1. Let's take a look. I think I left it open. I thought I did. Perhaps not. Doesn't look like I did. Well, in any event, we can go ahead and open up a new connection. So we'll go to remote desktop. What's going on here? Why am I not seeing the whole screen? All right, well, let's go to PC2. I thought I had left that open, but we're going to go ahead and connect back to our server, 10.1.5.100. All right, and we're going to go into our forward lookup zone back into CLL Collab. And now what we're going to do is we're going to add a lookup zone, or we're going to modify the lookup zone to add our SRV record. So we're just going to right click and we're going to say, let's go ahead and add other new records. And here we can select different types of records like an alias or delegation signer and so on. But specifically, we're looking for CNAME. There's the mail exchanger record for email, additional pointer records and so on, but we're looking for service location. I keep calling it server because SRV to me is always like server, but it's actually technically a service record. So we're going to go ahead and create this new record. The service is going to be underscore XMPP client. So let's find that here. Should be listed here. Why am I not seeing it? Interesting. I should see service of XMPP client. Why am I not seeing it? I guess I just have to kind of type it in manually here. I thought it was going to be listed, but we'll go ahead and put it in statically. It's going to be a TCP-based application. It's going to use port 5222 by default. And this is defined by the CMS configuration, right? CMS CLL-collab.internal. All right. And the idea here is that we're establishing an SRV record for this particular service. So we'll go ahead and save that and click done, and we can see that that service has been created. Specifically port 5222 for cms.cll-collab.internal. All right. Now task 4, we're not using that record in this particular case, but we wanted to at least identify how it was configured. In task 4, we want to configure and troubleshoot NTP on our Cisco router. NTP plays a really significant role within the unified communications architecture. The phones, as we talked about in our lecture portion, the phones will utilize MTP for their date and time. Certificates will rely on NTP to identify the validity period of a particular certificate, or at least to identify the time, which would then indicate whether a certificate is valid or not. And time is also used for other synchronization aspects as well. So it's extremely important within a UC environment that we have an adequate time source. In fact, Cisco recommends that you have at least, or at most, a stratum level of 3. Anything above 3 would be considered unreliable, or at least potentially unreliable, and we should try to avoid using those higher stratum numbers. So we know generally what NTP does. The Network Time Protocol delegates time synchronization or provides time synchronization in the network. That NTP source is usually going to get its time from an authoritative time source like a radio clock or an atomic clock that's attached to a time server. NTP and then in turn is going to distribute that time across the network. NTP, as I've already mentioned, uses these different stratum levels to describe how many NTP hops away a machine is from that authoritative time source. A stratum of 1, for example, means that we have an authoritative time source directly attached. A stratum of 2 means that we're getting our time from another device that is a stratum 1, and so on. So each time I move further away from the original source of information, I'm going to increase that stratum number by 1. NTP has 2 different ways of avoiding synchronization to a machine whose time may not be accurate. NTP, for example, will never synchronize to a machine that is not synchronized itself. And that information is actually provided in the NTP message. NTP is going to compare the time that's being reported by multiple machines, and it's not going to synchronize to any machine that has a completely or significantly different time than the other devices, even if it has a lower stratum number. Generally, the lower the stratum number, the more preferred that particular time source. All right. Now, to understand the overall NTP process, we also have to understand the fields that we're going to see, and we're going to run this command in a minute to take a look at it, of the show NTP associations command. All right. So an asterisk in the field will indicate that we're synchronized to that particular peer. The pound sign will indicate that we're almost synchronized to that particular peer. The plus sign indicates that the peer is selected for possible synchronization, but we haven't yet synchronized. The dash would indicate that is an NTP candidate, and the tilde symbol, the little squiggly line above the apostrophe on some keyboards anyway, is that the peer is statically configured. All right, we're going to use the command. We're going to specify the address. We're going to specify the reference clock, the stratum number, the polling interval. By the way, the polling interval is reported in seconds. That interval usually starts with a minimum of 64-second poll intervals, and then we go from there. All right, and we can increase the steps all the way up to 1,024 seconds if we want to reduce the overall network overhead. We cannot adjust the NTP poll interval on a router because that's determined internally by different algorithms. All right, so we're going to go ahead and open up a PuTTY session, and we're going to go over to router 1. Let's go ahead and minimize this device. It doesn't really matter which router we're going to, or which machine that we're going to use, or computer we're going to use to connect to the device. 10.1.5.252. We'll accept the signed certificate. Administrator. Pretty much have the same. Oops, that's not going to work. Let me do a restart session here. I'm going to duplicate the session. Administrator and C0LL at Bravo. All right, so the first thing I want to do is I want to see if NTP is even running on this device. So I'm going to use the command show NTP status, and that will tell me if the device is even running NTP, which, by the way, in most modern iOS, it is running by default. So this is kind of rare that we would see an iOS device not running NTP. If I do a show version, this is XE version 3.16. That's relatively new, so somebody must have actually just gone and disabled NTP. All right, so let's go into configuration mode. All right, and we're going to set NTP on this router, and we're going to say NTP master, NTP master, and we're going to specify our stratum number. Now you'll notice it goes from 1 to 15. 15 being the worst and 1 being the best. 16 is unreachable, so any device that's advertising a stratum of 16 would not be synchronized. So we're going to set it to 15 for now, putting it at the worst, and we're going to do a show NTP status just to see what the effect of that particular configuration is. All right, we can see that the clock is unsynchronized. Well, it's actually technically synchronized in this case, but the reference is a loopback interface, right? 127.127.1.1. Basically, that just means that the router is using its own internal clock as the time source. And although the time it shows is synchronized, right? Oops, we lost our connection already? No. Although the time shows as synchronized, it may show up as unsynchronized initially, as long as we're measuring the drift in time. And actually with NTP, even though it's a relatively basic protocol, it could take anywhere upwards of 15 minutes for that synchronization to take place. All right, so let's go ahead and verify the NTP service configuration. Let's get out of config mode here, and we're going to do a show NTP associations. And we can see that 127.127.1.1 has the asterisk, which is up here. It has the tilde, which means that it was statically configured. The reference clock is a local clock. We're identifying the stratum as stratum 14, which is one less than what we configured, right? NTP master 15 is what we put in the router. The router pulls its own internal clock, and that clock is never unreachable. All right, we see a reach of 77. That means that the NTP process received a certain number of bytes, right? That's an octal format, meaning that 77 needs to be converted to binary, which would indicate how many bytes it's received. All right, now what we're going to do is we're going to go ahead and specify the actual NTP server of our domain controller. So we're going to go config T, and we're going to say NTP server, and we're going to specify the domain controller as our NTP server. All right, and again, it could take a little bit of time for the NTP drift to be recognized, and then for the router to be synchronized to that server. But let's go ahead and check it anyway. Show NTP associations. And we can see that 10.1.5.100 is in fact providing time. Well, it doesn't have a asterisk next to it. That should eventually change. Again, it might take a little bit of time, but we can see the reference clock for that source is 10.1.5.254, which is the router in our network. It's reporting a stratum of 2. All right, we're still trying to calculate the drift. But once the drift is calculated, we should switch over to that server because it has a lower stratum number. All right. All right. Well, we finally got to the point where we were synchronized. We can see that the asterisk is next to the 10.1.5.100 now. So if I do a show NTP status, I should see that the clock is synchronized. The reference clock is 10.15.100. Notice here that the stratum is 2. That is the stratum that's being reported by 10.15.100. Our stratum is stratum 3 because we're the next hop in line. All right, so we have a couple more tasks here. The next task is going to be to configure and troubleshoot NTP on our Unified Communications Manager server. So let's go back over to our other PC here, PC1, and we're going to go ahead and log into OS administration. All right, I actually think I'm already logged in here, but let's take a look. Yeah, I'm already logged in. When we go to OS administration, we can adjust the NTP reference within Call Manager from here as well. Keep in mind there are two places within Call Manager that you can set an NTP reference. You can set an NTP reference for the phones themselves. We call that a phone NTP reference, and that is going to be for the SIP endpoints that are registered to Call Manager. And then we can go under OS administration and we can identify the NTP server by going to settings and NTP servers. This is going to apply to the system as a whole, and it's also going to apply to our skinny endpoints. So the first thing we're going to do is we're going to go ahead and add kind of an invalid NTP server for the purposes of kind of just verifying if we had accidentally typed in a wrong NTP server in our configuration, or for some reason this particular NTP server was accessible at one point and now it's no longer accessible. And so we're gonna make this use this as an example for troubleshooting. All right. So we can see here in this case that 10.16.252 is not accessible. So what we're going to do now is we're going to do some basic troubleshooting on our Call Manager server in the command line itself. So we'll go ahead and connect to our Unified Communications Manager server. We're logging in with the OS administration account in this particular case. It's the same account that we would use to log into OS administration on in the GUI interface as well. And we can use a couple of different commands to verify NTP. The first command that we can use is a utils NTP status command. That will show us the status of NTP, and sure enough we see that invalid server listed there, 10.1.6.252. We can actually see that it's kind of stuck in the init state and it has a stratum of 16, which means it's unreachable. All right, we can actually come in here and do a diagnostic as well. We can go utils diagnose module NTP underscore reachability, and we will be able to see additional information about this particular issue. Let's see, what did I mistype this time? Diagnose. All right, let's fix that. Utils diagnose module NTP reachability. What it's going to do is it's going to give us some details on why this particular NTP server doesn't appear to be functioning. All right, we can see here that the NTP service is showing as down. Well, it's kind of listed as the NTP service is down. We can see that right here actually. All right. There's some additional information that we can pull from a log file if we need to, but we're not going to do that in this particular case. All right, so now what we're going to do is we're actually going to do a packet capture. And this will allow us to do console captures based on the port or the protocol that we specify. So we're going to do a utils network capture. And specifically, we're going to look at port number 123, which is UDP. And that's our NTP information. We can see that we're collecting NTP information from our Windows server. That's the one that's actually providing us information. We can actually see from this output that not only are we sending the information, but we're actually getting the information back right here, right, in the opposite direction. All right. We can also see in the case of our 10.1.6.252, we're sending information, but we're not receiving any information back from that particular device. All right. So again, this is a way for us to kind of identify, whether or not we're actually even receiving NTP packets or even sending NTP packets to that particular endpoint. So let's go back to our call manager. We're going to delete that invalid server from the list. So we'll highlight this one and say delete selected. Let me scroll up here. And we're going to delete that NTP server. And then we're going to go ahead and add a legitimate server, 10.1.5.252. And we should see based on that, that we're going to collect information from that server. All right, and then we'll see how that's going to affect our association within Call Manager. All right, so we're going to go ahead and add a new one, and it's going to be 10.1.5.252. We'll save that. All right, we can see that this NTP server is actually accessible. It is a legitimate NTP server in our domain, and we can see from this particular output, eventually we'll see that we're going to get information from 252. Right now well actually there's one right there. Right here we see that we actually sent information to 10.1.5.252, and we received that information from 10.1.5.252 right here. All right, so that's good. That means that we are confirming that NTP is working from that particular device. Now if I do a Control-C, we'll go ahead and stop the capture. And let me scroll back down here because we've got a little bit of information. And we're going to use the utils NTP status. Status. And we can see that 10.1.5.254 is configured, as well as 10.1.5.252. We see a stratum of 1 for 10.1.5.254. And we see a stratum of 3 for 10.1.5.252. Now, it hasn't quite synchronized yet, again, because it takes quite a bit of time. It took probably a better part of 30 minutes or 40 minutes, actually, for the other time to synchronize. I just paused the video and kind of let it happen, and it took a long time. So you have to be really, really patient when it comes to dealing with NTP and synchronizing the clocks. There's really no way to force it to do it any quicker. You just have to be patient. I've run into a lot of scenarios, like I said, where I think I've misconfigured NTP or whatnot, and I go back and reconfigure it, and I'm ending up kind of starting that clock over again, which is totally counterproductive, obviously, to what we're trying to accomplish. All right, so we'll just assume that's going to work. We know that that time source is providing time. So eventually it will synchronize, all right? It will eventually synchronize. So now what we're going to do is we're going to go into our switch and we're going to take a look at our CDP configuration and our LLDP configuration. Again, there's really no reason to run both. Let me log in here. CDP, of course, is Cisco proprietary, whereas LLDP is an open standard. Oops, dang it. Didn't hit the return key there, so let's duplicate that session. Let's close that one out. Yeah, let's end that session and COLL at B. Ah, dang it. COLL at capital B. There we go. All right, so if I do a show CDP, I can see CDP is not enabled. If I do a show LLDP, I can see LLDP is not enabled. Now, on Cisco switches, LLDP would not be enabled by default anyway. Only CDP would be enabled by default. But in this particular case, it's been disabled just for the purposes of this exercise here. We know that at least one of those two protocols is going to be necessary for us to do discovery by the phones of what voice VLAN they belong to. And then in the case of LLDP Med, it's going to be necessary that we're running that protocol to be able to provide additional information about the type of device, the amount of power that's required, and so on that device for it to be able to communicate that information to the switch, and then the switch can take the appropriate configuration actions. There's a couple ways to enable these protocols. Certainly you want to enable them globally first, so we're going to go ahead and type CDP run and LLDP run. And that will enable those protocols globally on the system. All right. Now, it doesn't necessarily mean that they're running on the interface. By default, we don't have CDP disabled on the interface, so it should run on the interface. But if I do a show run interface gig 01, do show run interface gig01, we can see that CDP and LLDP are actually turned off on the interface. This is a configuration that was applied for the purpose of this exercise. So if I do a show CDP neighbor, I do see some CDP information for the other ports that are connected to the switch, but I don't see any of the CDP information for the physical phones that are connected to gig01 and gig02. So I'm going to go into interface range GI01-2, and I'm just going to say CDP enable. We use the CDP enable command on, I'm surprised it took that. We use the CDP enable command on the interface to enable CDP explicitly on the interface. We also do use the LLDP transmit and the LLDP receive command to enable LLDP on the interface as well. You have to run CDP or LLDP globally if you want to run them on the interface. You can't explicitly enable these protocols on the interface, but you can explicitly disable the protocol on a per interface basis. But you cannot say, for example, turn off CDP for the whole device and then go and turn it on an interface. So if your goal is to only have this protocol running on one or two interfaces, then what you're going to have to do is you're going to have to go in and essentially disable it on all the interfaces that you don't want to run it on. All right, so now let's do our verification. So CDP neighbor, we see the two endpoints, SEP09 Echo and SEP Delta 2 Charlie. SEP is Celsius Ethernet phone, and that's just the company, again, that manufactured this equipment originally that Cisco acquired. And if I do a show CDP entry, I can go ahead and copy one of these names, and I can see some details about that particular device. This happens to be an 8865 phone. It's connected to gig02 on port 1 of the phone. The secondary port is shut down. It's running firmware SIP 8845.65.11.7.117. And we can also see some of the power information. It's requesting power, power ID2, the different power levels it supports. That's information that the switch understands. It's not necessarily written in layman terms, for example. But if I did a show LLDP entry, and I looked at the same entry, let me go ahead and copy that again. And I looked at the same entry, I can actually see specifically how much power this device is requesting. In this particular case, 12.5 watts. Also notice here in this case with LLDP, I'm getting other information. What is the phone model? Who is the manufacturer? What is the serial number? What is the firmware version? What is the software version? What kind of voice quality of service tagging and QoS configurations being applied? The voice VLAN that it belongs to, IP precedence or priority of 5 for layer 2 classification, and DSCP EF expedited forwarding, or DSCP 46 for layer 3 marking, and then for the signaling traffic, a priority of 4 and a DSCP of 32. This is the information that's actually carried in the LLDP MED information, that media device information, those additional TLVs that we have within LLDP to carry this information. So we can see that we're getting some very, very useful information about this particular device. All right, so that kind of wraps up this discovery. We didn't get into SNMP or LDAP, but we will talk about those protocols a little bit later on. We certainly talked about NTP, DHCP, DNS, TFTP, at least from the perspective of how do we configure that within the scope of DHCP. We didn't specifically get into the details of DHCP or TFTP as far as its operation. Let me see, I wanted to check one more thing real quick, just to see if we synchronized yet. Nope, we haven't. I had hoped that we would, but we didn't. We did also talk about LLDP, specifically MED, LLDP MED. All right, so we're going to wrap up this discovery We're going to get into our discussion of codecs, and we'll wrap up the whole module by going through our summary challenge, and then we'll move on to call signaling over IP networks. So what is a codec? A codec is it's basically a device, typically a hardware device. It is a codec is what they call a portmanteau of coder decoder, right? Kind of a combination of the coder decoder word. And we have different types of codecs within the system. When you're speaking into a phone, you're generating something called a pulse amplitude modulated signal, an analog waveform, right? But we have to be able to take that analog waveform and we have to be able to convert that analog waveform into a pulse code modulated signal. All right, let me make a couple of notes here. So you have this pulse amplitude modulated signal, which is your analog waveform. All right, and that needs to be converted to a digital format. All right, and that's what we call a PCM signal, or a pulse code modulated signal. All right, that's your ones and zeros, right? This process is what the codec is responsible for. The very first codec that was ever used was built by Texas Instruments, and it was in the Speak and Spell, where you could actually push a button and spell words and whatnot. I'm sure a lot of you had Speak and Spell at one time in your life, but that's the very first device that had a consumer grade codec in it. All right, and we'll talk about the different types of codecs. There are audio codecs, there are video codecs, and so on. But the whole process of converting a pulse amplitude modulated signal to a pulse code modulated signal is a process called quantization. All right, now I'm not going to get into the details, but I'll give you some of the high points of the quantization process. So we're taking this analog waveform and we're putting this analog waveform on a quantization scale. All right, now if you can imagine, that scale has steps and it has segments. Let me kind of draw this out as well. So if you can imagine, you've got kind of this line. Oops, let me do that again. You've got this line that goes this way, and you've got this line that goes this way, and your waveform kind of sits on this scale. All right, I'm not drawing a very good, I don't have my touch screen with me right now, so I'm kind of doing this with a mouse. And then that scale is a way for us to essentially quantize the signal. So you've got these things called steps and segments, and this is a logarithmic. That's logarithmic. I don't know if that's how you spell it. It's L-O-G-O, I think. Logarithmic. Is that right? I don't know. Scale, right? So you've got, in essence, on that vertical axis, you've got 16 steps. You've got 7 segments. So 0 through 7. And then in between those 7 segments, you've got 16 steps in each segment. All right, so going back to this diagram here, if you can imagine, we have these steps which are logarithmic. So as you go up, they're further apart. As you get closer to the 0 axis, they're closer together. And this is the 0, this is 1, this is 2, this is 3, this is 4, 5, etc. Right? So here's kind of a better diagram of what I was describing there. It's not the whole scale, but it provides you at least an idea here. So we can see segment 0, segment 1, segment, well, that should say segment 2, not segment 3, but that's okay. We'll just erase that. All right, that should be segment 2 and so on. So if you can imagine, and you can see that this diagram is actually not as great as I thought it was going to be, but it'll give us a good idea. All right. On the left side, we have essentially the what we call the scale, if you will. All right, and the idea is that we have these 7 segments which are not evenly spaced as the diagram suggests. They're not evenly spaced next to each other, but and if you think about it, why would that be, right? Why would I have, for example, let me go back here. Why would I have on this scale, I can use this tool here now. So here is segment number 1, and here's segment number 2, and then segment number 3, and then segment number 4, and segment number 5. Why would I have them closer together towards the 0 on the scale as opposed to further apart as I go up the scale? Well, if you think about it, speech and human perceptible speech, you're going to have more data points at lower amplitudes and lower frequencies than at higher amplitudes and higher frequencies. So we're going to get more data points at those lower frequencies, which means that we want to have smaller gaps between the quantization points on the scale at that particular level. So again, let me change that black there. So if I'm looking at this scale, so this is my scale, there's my 0 point, and here are my individual steps. So step 1, segments, excuse me, segment 2, segment 3, segment 4, segment 5, segment 6, and then all the way up here, segment 7, if that makes sense. All right. And then in between each of these segments, we have the steps. Now the steps are linear. There's actually 16 steps in each segment. I'm not going to draw all of them, but you can imagine inside each of these, there are 16 segments, steps, excuse me. I keep getting those terms backwards. All right, so that's linear within the group. All right, now if you can imagine, I've got my waveform. Let's use this tool. I've got my waveform here that I'm putting on this scale. And that waveform allows me to, that's my pulse amplitude modulated signal. Now going back to the quantization process, what we do is we base our, well, what we're doing is we are trying to create a digital representation of an analog wave. All right, that's our goal here with this particular concept. Now the idea, of course, is that we want that digital representation to be high quality, right? We want to be able to say, okay, we've created this digital representation of this analog waveform. It needs to accurately represent that analog waveform, right? I don't want it to be lossy. I don't want it to be missing context. I don't want it to be noisy and so on. And so we use something called Nyquist's theorem to define how we sample the pulse amplitude modulated signal. All right, and Nyquist's theorem states that in order to create an acceptable and I'm paraphrasing here, right? Representation of the PAM signal, we need to sample the PAM signal at twice the highest frequency. All right, so human perceptible speech is anywhere from 400 hertz to 4 kilohertz. 4 kilohertz. All right, there are some varying thoughts on that, but generally speaking, that's what most people kind of agree on. So the highest frequency of, human perceptible speech is 4 kilohertz, which means we are going to sample at 8,000 times per second. That's our sample rate. So that means I'm taking this waveform and I'm dividing that waveform up into samples, and over a 1 second period, right? Over this 1 second period, probably could have done this an easier way, but it's all right. Over this 1 second period, I'm generating 8,000 samples. All right. So that means I'm slicing this waveform into 8,000 slices. All right. This is a horrible diagram, but you get the idea. These become my reference points for each of the samples, and then I reference them on the scale. So this point, this point, this point, this point, this point, and so on. You get the idea. And all I have to do now that I have all of my reference points of the pulse amplitude modulated signal, is I now want to convert those reference points into some sort of digital output. Now, if you think about it, we have a plus on the quantization side. We have a plus and minus 0 reference, right? Is it above the 0 plane or is it below the 0 plane? So that would be my first bit. So we'll say it's, depending on the encoding method, whether we're using U-law or A-law or whatever, but we'll just say on the plus side it's a 0, on the minus side it's a 1. Then I have my segments, and there are 8 of those segments, right? 0 through 7. 0 through 7, sorry. So how many bits do I need to represent the actual segment? I need 3 bits to represent the segment. All right. And then within the segments, I have 16 steps, 0 through 15, and I need 4 bits to represent those steps. Does that make sense? So when it's all said and done, I have the first bit that represents the plus or the minus scale. I have the next 3 bits. Let's say it's in segment number 2, so that would be a 0, 1, 0. And then it's on step 12, right? 1, 1, 0, 0. So this is my 8-bit per sample conversion or output. So this is my pulse code modulated representation of that particular reference point on the scale for my pulse amplitude modulated signal. Well, guess what? I'm doing that 8,000 times a second. 8 times 8,000 is 64 kilobits per second of information. So that's basically a DS0, isn't it? A DS0 is a way for us to describe simply a single, for lack of a better term, a single analog circuit. Or at least a channel on a PRI or a channel on a T1 or whatever. 64 kilobits per second. All right. So you're going to see a reference to this idea of quantization. They don't really get into the whole mathematics of quantization on the exam, but that's essentially what the goal of a codec is. It's to take that pulse amplitude modulated signal and take that signal and convert it to a pulse code modulated signal. Different codecs do it a different way. There's also different companding techniques. There's mu law, which is what we use in the United States, and there's A law, which is used everywhere else. Well, Japan uses the same as the United States, but and then there are different types of codecs that will compress the bit rate, by using some sort of compression technique, and so on. All right. So in essence, what is a codec? Right. The codec is what we're doing in this particular case. Right. It encodes and decodes the audio, and of course we also have video codecs as well. All right. Now we say that it compresses and decompresses that audio data as well, depending on the audio coding format that we're using. There are some codecs that do provide compression and decompression components, but there are also some codecs that don't do that. Right. G7.11, for example, is an uncompressed audio codec. But the idea is that we're trying to create this pulse code modulated representation of the pulse amplitude modulated signal with as few bits as possible, but we're still trying to retain the quality, because what's going to happen at the other end of the call? At the other end of the call, that PCM signal needs to be converted back into a pulse amplitude modulated signal so it can be played to the earpiece so that we can hear that audio in our eardrum, right? Pretty soon, in the near future, we might not even have to do that. We'll just plug in our brains and we'll just do everything digitally. But for now, we have to do with analog waveforms. All right. So most codecs are implemented as libraries, and these libraries have different types of transforms that they can run. So there are several different codecs that exist. We have lossless compression codecs, no compression codecs, lossy compression codecs, and so on. I don't know if I really want to get into the specifics of each of the different types of codecs. I guess we definitely should probably talk about some of the common codecs that we see in the Cisco space. But based on what we're seeing, let's go through what they have here in the book first, and then I'll probably get into a little bit more about the codec information. They do mention a few of the codecs in the book here. These are some of the very, very common codecs that you would see within a Cisco solution: a G.711 codec, a G722, G729, Opus, ILBC, ISAC, and so on. All right, now we will get into this in a little bit more detail later on, as to what, how these codecs are used and what the end result of a particular codec is, as far as the amount of bandwidth and whatnot that's being utilized by the codec. But the most of the codecs that we're using are going to provide a certain amount, or going to require a certain amount of bandwidth if we're using that particular codec. So for example, a G711 codec is an uncompressed lossless codec. So it's going to generate a raw bit rate of 64 kilobits per second. Now, the other thing to think about is that Cisco does different sampling as well. We don't actually encode 1 second of information in one packet. We encode 20 milliseconds of data, or 30 milliseconds of data, or 40 milliseconds of data within a particular packet. So if I'm doing a G711 codec, for example, and I'm doing a sample rate of 10 milliseconds, that's going to generate about 80 bytes of data in that codec itself. If I'm sampling at a sample rate of 10 milliseconds. If I'm sampling at a voice payload size of 20 milliseconds, which is pretty typical with Cisco. Cisco generally operates on a 20 millisecond sample size or 30 millisecond sample size, I'm generating 160 bytes of data. All right, the math works out, right? If you think about it, it's still 8 kilobits a second if I'm doing a whole second of, sampling a whole second of information. But again, I'm only taking a fifth of that. I'm only doing 20 milliseconds, which is going to generate 160 bytes of data. That doesn't include the overhead, by the way. That doesn't include the encapsulation and so on. That's going to generate about 50 packets per second of data, which is going to generate about 87 kilobits a second of bandwidth, or require about 87 kilobits per second of bandwidth. Again, minus the overhead. Now, if I go to like a G729 codec, that's what we refer to as an 8 kilobit per second codec. It's only going to generate, at a 20 millisecond sample size, it's only going to generate 20 bytes of data. Okay? So you might say, well, wait a minute, why wouldn't I just use a G729 codec? If it's generating only 20 bytes of data, and we're able to convert our analog waveform into a digital signal, well, there are two things to consider when you're considering a codec. One is loss, right? We must be losing something if we're only generating 20 bytes of data in our voice payload size as opposed to 160 bytes of data for a G711 codec. Well, and that's true. We measure the quality of the codec with something called a MOS value. MOS stands for mean opinion score. And essentially it's a scale of 1 to 5, 3.9 being considered toll quality, meaning that it's kind of, you know, the digital signal that's being generated by the conversion process is high quality and very little loss and very little perceived loss in the actual audio that you're hearing. Well, a G711 codec has a mean opinion score of about 4.3, so it's above toll quality, whereas a G729 codec has a mean opinion score of 3.7, so slightly below toll quality. So again, there's a trade-off. Now, will you be able to tell yourself, you know, yeah, if you were listening to the same conversation in each ear, you might be able to tell the difference between G711 and G729, but the reality is that you probably, you know, separately and independently, you probably wouldn't be able to tell much of a difference. All right. So again, you might go back to this idea of, well, okay, if I can't really tell, why wouldn't I just use a G729 codec? Well, G729 codecs use compression and decompression, which takes time. So it takes time and it takes resources to compress the audio stream and then decompress that audio stream, as opposed to not doing anything but simply quantizing the audio stream. So there's a trade-off there. So we use G729 codecs when bandwidth is a concern. When we don't have a lot of bandwidth, instead of 87 kilobits a second per call, we're only generating about 31 kilobits a second per call. But there is that trade-off. All right. Now they mentioned G722. G722 is also a 64K codec. So it's going to operate much like G711. There are some additional benefits to running it. It has a lower mean opinion score than G711, but it's like 4.1 or something like that. But it has some other functionality. So generally speaking, G722 and G711 are almost always classified as the same. ILBC, there are a couple of different versions of ILBC. There's a 15K version and a 13K version. ILBC is actually a really, really good codec because it only generates about 40 bytes of data, about a 38 kilobit per second stream, but it has a mean opinion score of 4.1. So it's above toll quality, but it's not quite as efficient, or at least bandwidth. It's a little bit more bandwidth intensive than a G729 codec, but you know, you get that toll quality. And there's others. There's G726, there's G726 32K, and G726 24K, there's G728, 16K. But for the most part, I think what you're going to see in your environment is either a G720, a G711 or G729. Those are the two most common codecs that you're going to see in a kind of a Cisco voice environment. You do have an option though. Cisco does support lots and lots of different types of codecs. We use locations and regions in the Cisco configuration to define the codecs that are going to be used. Well, we use specifically regions to do that, to define the codecs that are going to be used on a call, and then locations will allow us to define how many calls are allowed, between the different locations. We'll get into that in a little bit more detail later on. We also have different video codecs as well. But again, the whole point in this particular case is not that we are going into detail. I mean, I've obviously gone into a lot more detail than the book here, but is what is the general purpose of a codec itself? All right. Now, a G722 codec, a G711 codec, these are codecs that you typically would use within the LAN. Because of the amount of data that they generate. The PCM process generates 64 kilobits of data for the G711 codec. G722 is a ITU-T standard just like G711, but it has different variants. It can operate at 48 kilobits per second, 56 kilobits per second, or 64 kilobits per second. Is a wideband codec as opposed to G711, which is a narrowband codec. So that is pretty important. I'll get into the details of wideband versus narrowband a little bit later on. G729 is a compression-based codec, requires a lot more resources. It's considered a high complexity codec, meaning that it has to have a lot of hardware and processing components to process it. By the way, we use something called DSPs to be able to do this coding and decoding. A DSP is a digital signal processor, and they're built into the phones, they're built into router hardware, and that's what we use to do the coding and decoding. All right. Now there are different variations of G729. As I said, it's an 8 kilobit per second codec, but it does require a lot more resources. There is an NXB version, what we call G729B, but it's basically the same as G729A. The only difference is that G729B adds things like voice activity detection. So we can get rid of about 30% of the bandwidth requirement for the coding process and decoding process if we take out the white space, right? And it's still there, we just don't encode it and send it as data. That's what voice activity detection is. Provides us the ability to reduce the amount of bandwidth by simply not encoding when there's no audio. Another component of the Annex B variant is CNG, comfort noise generation. In traditional voice conversations, when you had a phone system, you always had the idea, you always knew that you were connected on the call because you could hear that white noise in the background. All right. Now, if I'm using VAD, the white noise is not being encoded. All right. In general, the voice quality is so good that you might not even hear noise. So comfort noise generation is a way for us to insert that noise into the audio stream, so that the person on the other side thinks that they know that they're still on an active circuit, they're still on an active call, and the call hasn't disconnected. It's kind of an interesting concept, right? So again, with VAD, we can save 30 to 35% of the bandwidth. But again, implementing these features takes more resources because we have to have algorithms and processes that that implement these particular features. All right, ILBC is a narrowband codec, generates a payload of about 13K. It's very much like 729A as far as complexity requirements, but it has a higher mean opinion score and higher quality. All right. All right. We might get into some of the more details about these codecs a little bit later on, but I think I'll leave it at that for now. Certainly, you can go online and look at all kinds of codec information online. But which option is an example of a video codec? Well, 711, 722, and 729 are all audio codecs, so H.264 is a video codec. Video codecs perform basically the same function as the audio codec. Obviously, in the case of a video codec, we're having to encode audio and video, and it's kind of a completely different area, but it's the same general concept. Our goal is to be able to take some sort of analog signal and convert it to a digital pattern so that we can transmit it over the network, and then on the other side do the opposite and decode that information. All right. All right, so the only thing that we have left in this section is to go through our summary challenge. So the first question is, which component of the Cisco collaboration architecture provides conferencing? Well, that would be our meeting server, right? Unity Connection is our voicemail platform, Prime Collaboration Deployment is our management platform, and Unified Communications Manager is our call agent and endpoint registration platform. Which option is a valid Cisco collaboration deployment model? We can do, well, on-premise, hybrid, or cloud-based. Those are the three choices. So standalone doesn't make any sense. Co-resident is just a matter of installing the different VMs on a same physical platform, and a distributed deployment is where you have, you know, clustering over a WAN or servers that are clustered in different locations. So in this particular case, they're referencing the difference between what is a hybrid model, what is an on-premise model, what is the cloud-based model, which we talked about in the beginning of this section here. How many IAM and presence nodes can belong to a subcluster to provide redundancy? Now, we didn't actually get into this, but we can have up to 9 servers within a call manager cluster. Each of those servers can act as subscribers or one publisher and multiple subscribers for call processing and as call agents. But when it comes to Unity Connection and when it comes to IM and P, you can only have a primary and secondary node. All right, so the answer in this particular case is, even though I might have 5 nodes within my UC cluster that are operating as call agents, only 2 of those nodes can act as IM and P servers. And by the way, you would actually deploy them as, you don't run IM and P within Call Manager. You either have a Call Manager node or you have an IM and P node. They're completely separate operating systems. They're installed differently. All right? But the answer is 2, primary and secondary. Which tool guides the user through a complete system deployment? We talked about that, actually downloaded the tool. I kind of started to go through the process. It's the Cisco Collaboration Sizing tool. All right. What are the advantages of using MTLS rather than TLS? Well, mutual is the term there, right? M stands for mutual, which means that we're going to authenticate the server to the client, and we're going to authenticate the client to the server. So in this case, the answer would be A. Where's my mouse? There it is. Would be A. MTLS uses two-way authentication. The server also authenticates the client. All right. What type of DRS option does Cisco Collaboration support? Semi-automatic, incremental, differential, or automatic. I'm not sure what they're really asking here. I guess they're just asking, can I do a manual backup or do I do automatic backups? I don't know what semi-automatic would be in this case, but automatic backups. Can we do incremental and differential backups? No. When we schedule our backups, we actually define what we want to back up. There's a little check boxes. We can say, okay, back up the CDR records, back up the CMR records, back up the publisher, back up the subscriber, those kinds of things. But we don't really get we can't really define specifically what file level components get backed up. All right. Which component of the dial plan ensures that calls are not dropped without being answered? That would be call coverage, right? Call routing and path selection is basically how the calls get routed. Digit manipulation is ANI and DNS manipulation. Calling privileges are partitions and search spaces. All right. Which protocol do Cisco IP phones use to obtain their configuration files? That is TFTP. Or HTTP or HTTPS if it's a newer phone model. Which audio codec uses compression to provide a high quality, mean opinion score of about 3.8 or 3.9, 8 kilobit per second voice call. And that is our G729 codec. Okay? All right. So we'll wrap up this section here. And we'll see you guys in the next section, which is exploring call signaling over IP network.